Right now, as you read these words, you are hurtling through space at a speed of roughly 230 kilometers per second, not because of anything humanity built or launched, simply because you exist on a planet that orbits a star, and that star is itself in motion, sweeping through a vast structure of gas and dust and ancient light that has been turning slowly for longer than the Earth has existed. You are a passenger inside something enormous, something so enormous that even the scientists who study it have struggled for generations to measure its true size from the inside. That structure is called the Orion Arm, and there is a very good chance you have seen it drawn on a diagram at some point in your life. A labeled map of the Milky Way, viewed from above, with sweeping colored curves representing the major spiral arms and a short, thin connector sitting between two of them, a modest bridge, almost an afterthought, and somewhere along that thin bridge, a small marker, an arrow, a label that says, "You are here." It looks insignificant. It looks like nothing. It looks like the kind of feature a cartographer might include only because leaving it blank would feel incomplete. And for most people who glance at that diagram for a few seconds before moving on, the impression it leaves is precisely that. We live in a minor part of the galaxy, a spur, a secondary feature, a small sliver of something much grander. But here is what that diagram has never once told you. That thin little bridge, that labeled afterthought, that minor spur sitting between two sweeping arms, is 10,000 light years long. 10,000. And if you could somehow travel at the speed of light, the fastest velocity the laws of physics permit, it would still take you 10,000 years to cross it from one end to the other. 10,000 years at the speed of light. And we call it minor. Tonight, you are going to understand what that actually means. Not as an abstract number filed away in some corner of your memory, alongside other large figures you have heard, and immediately stopped feeling anything about. You are going to understand it in your bones. You are going to see the Orion Arm for what it truly is, and you are going to understand exactly why every diagram you have ever seen has been, through no fault of its own, quietly deceiving you about the scale of the place you call home. If this kind of journey, the kind that fundamentally rearranges the furniture of how you see the cosmos, is something you value, then do me a small favor and hit the like button and subscribe to this channel. It costs you nothing but a moment, and it genuinely makes a difference in whether these explorations keep reaching people. Now, get yourself somewhere comfortable and still. Let's begin. To understand the Orion Arm, you first have to understand the structure it belongs to, because the Orion Arm does not exist in isolation. It is one feature inside a much larger system, and that system has an architecture worth knowing before we examine any single piece of it. That system is the Milky Way, our galaxy, the gravitationally bound collection of stars, gas, dust, dark matter, and stellar remnants that contains our sun, our solar system, and every single star visible to the naked human eye on any night in any place on Earth. You have heard the name, the Milky Way, so many times that it may have lost its ability to surprise you. It sounds familiar, comfortable even, but the object behind the name is anything but familiar. It is a structure so vast that its own light, traveling at 300,000 kilometers per second, takes 100,000 years to cross from one side to the other. It contains somewhere between 100 billion and 400 billion individual stars, and no human being has ever seen it from the outside. Not one. Every image you have ever encountered of the Milky Way as a whole, viewed from above, spiral arms sweeping outward from a glowing center, is an illustration, a reconstruction, an educated artistic rendering based on measurements taken from within the structure itself. We are inside the Milky Way, embedded within it. And that creates a problem that astronomers have spent the better part of 2 centuries trying to work around. Mapping the shape of something you are sitting inside of is genuinely profoundly difficult. Imagine trying to draw the floor plan of an enormous building while standing in one of its interior rooms. You can look out through windows, you can observe other parts of the structure in the distance, you can measure angles and distances to various landmarks, but you can never step outside, rise above the roofline, and see the whole thing laid out beneath you. You are working from the inside, always, with tools that were never designed for that task. What astronomers have pieced together through decades of radio observation, spectroscopic measurement, infrared imaging, and increasingly precise astrometric data is a picture of a barred spiral galaxy. That classification carries real meaning. It is not a generic label. It describes a specific and identifiable structure with distinct components, each one playing a different role in the galaxy's architecture. At the very heart of the Milky Way sits what is called the galactic bulge. This is a dense, roughly spheroidal concentration of predominantly old stars, crowded into a region approximately 10,000 light-years across. Stars in the bulge are packed far more tightly than they are out here in our region of the galaxy. If you were to somehow find yourself on a planet near the galactic center, the night sky above you would be nothing like the one above Earth. It would blaze, thousands of stars bright enough to cast their own distinct shadows on the ground beneath you. The sky would never reach true darkness. There would always be light, always stars burning in every direction you looked, many of them red and orange and ancient, having lived in the crowded heart of the galaxy for billions of years. Running directly through this central bulge is a structure called the bar. This is not a metaphor. It is a physical, elongated formation of stars, shaped roughly like a thick beam, cutting across the galactic core from one side to the other. Our galaxy's bar is estimated to stretch for approximately 27,000 light-years in total length, though that figure carries some uncertainty depending on the methodology used to measure it and the study you consult. The stars that make up the bar tend to be older and redder than the bright young stars found in the spiral arms. The bar is a prominent feature, and it is the defining characteristic that places the Milky Way in the category of barred spiral galaxies. Not every spiral galaxy has a bar. Some do not. Ours does. That bar shapes how gas flows through the inner galaxy and influences the behavior of the spiral arms that extend outward from its ends. Those spiral arms are the features most people picture when they think of a galaxy. The elegant sweeping curves of light, visible in photographs of other galaxies taken by instruments like the Hubble Space Telescope or the James Webb Space Telescope. Those photographs show face-on spirals with arms that seem to flow outward like streams from a central point, lit with the blue-white glow of young stars and the pink luminescence of ionized gas. The Milky Way has those arms too. We simply cannot see them the way we can see the arms of a distant galaxy, because we are not outside looking in. We are standing inside one of them, trying to infer the shape of the whole from our position within a single part. Now, before we go any further, there is something about spiral arms that most people fundamentally misunderstand, and correcting that misunderstanding is essential to everything that follows. Spiral arms are not solid structures. They are not walls. They are not rivers of stars moving in formation around the galaxy's center. If they were solid, fixed formations, they would have destroyed themselves long ago. The reason is that different parts of the galaxy rotate at different speeds. Regions closer to the center complete their orbits faster than regions farther out. A solid arm would be twisted tighter and tighter, with every rotation winding itself around the galaxy in an ever-tightening spiral until it eventually disappeared. The galaxy has been rotating for billions of years. Any solid structure would have wound itself into oblivion many times over, but spiral arms have persisted for billions of years. They exist right now, and they will continue to exist for billions of years more. This tells you immediately that they cannot be solid. They must be something else entirely. What they are is a pattern, a wave of density moving through the material of the galaxy, in much the same way that a wave moves through water. The water itself does not travel with the wave. The wave is a shape that passes through the water. Something very similar is happening in a spiral arm. The arm is a region where the galactic gravitational field creates a mild but persistent compression. Stars, gas clouds, and dust move through this region, slow down slightly as they pass through the denser zone, and then speed up again as they exit. The compression zone itself persists even as individual stars pass through and continue on their orbits. The best analogy is one you have almost certainly experienced yourself: a traffic jam on a major highway. There are stretches of road where traffic inexplicably slows to a crawl, then gradually picks back up. Then the road opens again, and drivers accelerate back to full speed. If you watch from a helicopter overhead, you would see a dense cluster of vehicles creeping along, with open road ahead and behind. Individual cars enter the cluster, slow down, and eventually emerge from the other side. But the cluster itself, the jam, stays roughly in the same location on the road. No single car remains in the jam forever. They all pass through it. But the jam persists because new cars keep arriving and entering the compressed zone as others exit. Spiral arms work on precisely this principle. Stars and gas clouds orbit the galactic center. As they move, they encounter the density wave associated with a spiral arm. They slow slightly, compress slightly, and in the case of gas clouds, this compression can be enough to trigger gravitational collapse. The compressed gas begins to contract. Denser regions within the cloud draw in surrounding material. Temperatures rise, pressure builds, and eventually, nuclear fusion ignites. A new star is born. This is why spiral arms appear bright in photographs of other galaxies. They are not bright simply because they contain more stars than the surrounding regions. They are bright because they contain more young stars. Massive, hot, intensely luminous stars that were recently born from gas clouds compressed by the density wave. These young stars shine with a fierce blue-white light, and they burn through their fuel so quickly that they die within a few million years. They never have time to migrate far from the arm where they formed before they explode or fade, so the arm is always marked by the newest, most luminous generation of stars. The older, quieter stars born in earlier passages through the arm have long since moved on to other parts of their orbits. The arm is not a wall of stars. It is a birthplace that keeps producing new stars, continuously, as long as there is gas available to be compressed. Understanding this is crucial, because it changes how you think about the Orion Arm. The Orion Arm is not a static feature sitting fixed in space. It is a persistent pattern of enhanced stellar density and active star formation defined by the density wave moving through our region of the galaxy. Stars within it are not locked in place. They orbit through it. Our Sun orbits through it. Over millions of years, the Sun's position relative to the spiral pattern shifts. We have likely passed through multiple arm regions over the course of the solar system's 4.5 billion year history. Right now, we happen to sit within the boundaries of the Orion Arm. That will not always be true, but for the entirety of human existence, and for millions of years before and after, this is where we are. The Milky Way has several major spiral arms. These are the dominant features of the galaxy's disk structure, the grand curves that define the overall shape of the system. Their names come from the constellations in whose direction we observe them from Earth, though the arms themselves extend far beyond those constellations in every direction. The Perseus Arm lies outward from us, farther from the galactic center than our position. It is one of the two primary arms in most structural models of the Milky Way, and it is an enormous feature, stretching for tens of thousands of light years in a sweeping arc around a significant portion of the galaxy. If you could somehow view the Milky Way from directly above, at a distance of millions of light years, the Perseus Arm would be one of the most immediately visible features. A bright, luminous curve of blue and white light tracing a grand spiral through the outer disk. Inward from our position between us and the galactic center lies the Sagittarius-Carina Arm. This is the other major arm in our region of the galaxy. When you look toward the constellation Sagittarius on a summer evening, you are looking roughly in the direction of the galactic center, and the Sagittarius Arm occupies much of the space between our position and that center. It is rich in star-forming regions, dense gas clouds, and young stellar populations. Like the Perseus Arm, it stretches for tens of thousands of light years in a curving arc around the galaxy. Then there is the Scutum-Centaurus Arm, which is by many measures the most massive and prominent arm in the entire Milky Way. It originates near one end of the galaxy's central bar and sweeps outward in a grand arc that may extend for 60,000 light-years or more in some models. It contains some of the most prolific star-forming regions in the galaxy, particularly near the inner end, where gas funneled along the bar's structure becomes dramatically compressed. Beyond the Perseus Arm, in the galaxy's outer regions, lies the Outer Arm, a sparser structure tracing the galaxy's fading periphery. And nearer to the galactic center, the Norma Arm occupies a region of higher stellar density, closer to the heart of the system. These are the major features, the grand architectural elements of the Milky Way's spiral structure. And between two of them, between the inward Sagittarius-Carina Arm and the outward Perseus Arm, there is a smaller structure, a connection, a bridge. Shorter than the arms that flank it, narrower, less prominent in the galaxy's overall pattern, this is the Orion Arm, also called the Local Arm, or by its older designation, the Orion Spur. The feature that every galaxy diagram places a small arrow on and labels, "You are here." Our Sun sits within this structure at a distance of roughly 26,000 light-years from the galactic center. That number is worth sitting with for a moment. 26,000 light-years. The light that left the galactic center when our Sun was in roughly its current orbital position has been traveling for 26,000 years. It began its journey at a time when the most sophisticated human technology on Earth was a sharpened stone. Agriculture did not yet exist. No city had ever been built. The wheel had not been invented. Writing was still thousands of years in the future. And the light that left the galactic center at that moment is only now, in this era, in this century, arriving at our solar system. That is how far we are from the center of our own galaxy. From this position within the Orion Arm, the Sun orbits the galactic center at approximately 230 kilometers per second. That is not a speed that connects to anything in ordinary human experience. At 230 kilometers per second, you could travel from one side of the United States to the other in under 20 seconds. You could circle the entire Earth in less than 3 minutes. And yet, even moving at this staggering velocity, the Sun requires somewhere between 225 million and 250 million years to complete a single orbit around the galactic center, one galactic year, one lap around the Milky Way. The last time the Sun occupied roughly its current position in its orbit, the first dinosaurs were beginning to appear on Earth. Humanity, with its cities and languages and technologies and accumulated history, is a phenomenon so recent that it does not even register as a rounding error on the timescale of a galactic year. Our entire civilization, from the first chipped flint to the spacecraft we have launched into the outer solar system, has unfolded in a span of time that represents less than 100,000th of a single galactic orbit. And through all those orbits, through all those billions of years of movement, the Sun has been a resident of the Milky Way, sometimes passing through denser arm regions, sometimes drifting through the quieter spaces between arms. Right now, it sits in the Orion Arm, and that location may matter more than most people realize. The spiral arms of the Milky Way are not merely aesthetic features. They are where most of the galaxy's star formation takes place. They are where the interstellar gas is most compressed, where molecular clouds collapse most readily, where the most massive stars are born, burn, and die most frequently. A planet orbiting a star deep within one of the Milky Way's major arms would exist in a dramatically more energetic and potentially more dangerous environment than Earth does. Massive stars explode as supernovae, releasing floods of high-energy radiation. The rate of such explosions near the densest parts of the major arms is substantially higher than in quieter regions like the one we inhabit. The Orion Arm, being a secondary structure rather than a major arm, is considerably less turbulent. There is star formation here, certainly. There are massive stars here, and there will be supernovae. But the rate and intensity of these events is lower than in the major arms surrounding us. The environment is calmer, more stable, more conducive to the kind of long, uninterrupted planetary habitability that seems necessary for complex life to develop. This observation is part of a broader concept that some researchers discuss under the term galactic habitable zone, the idea that the Milky Way is not uniformly hospitable to life. Regions too close to the galactic center are exposed to higher radiation levels, denser stellar populations, and more frequent disruptive events. Regions too far from the center lack the heavy elements forged in stellar explosions, elements like carbon, oxygen, silicon, and iron that are essential for building rocky planets and for the chemistry of life. Our position in the Orion Arm, at a moderate distance from the center and in a relatively quiet secondary structure, may represent something close to a sweet spot, far enough from the chaos of the inner galaxy to enjoy relative stability, close enough to benefit from the elemental richness that stars have spent billions of years producing and distributing through the interstellar medium. This is where we live, inside a barred spiral galaxy 100,000 light-years in diameter, containing hundreds of billions of stars, organized into sweeping major arms and smaller connecting structures, all rotating around a supermassive black hole at the galactic center, known as Sagittarius A star, which contains approximately 4 million times the mass of our Sun. Within all of that, we are here, in the Orion Arm, 26,000 light-years from the center, moving at 230 kilometers per second, taking 250 million years to complete each orbit. Every diagram that has ever shown you this arrangement has committed the same quiet deception, not out of dishonesty, but out of necessity. You cannot draw 100,000 light-years on a page and preserve the true scale of each individual feature. The compression required to fit a galaxy onto a screen or a poster is so extreme that every structure within it loses its true proportions. The galaxy's largest features look grand, its secondary features look minor, and the Orion Arm, this 10,000 light-year structure containing billions of stars and everything humanity has ever known or seen or touched, ends up looking like a sliver, a connector, an afterthought. But that is the diagram's failure, not the Orion Arm's. The diagram is a map, and like all maps, it sacrifices truth in some dimensions to achieve clarity in others. The sacrifice here is scale, and the cost of that sacrifice is that every person who has ever looked at a galaxy diagram and registered the Orion Arm as small has walked away with a fundamental misunderstanding about the place they inhabit. We are going to correct that misunderstanding completely and permanently, because once you truly understand the dimensions of the structure you are living inside, once the numbers stop being numbers and start being something you can feel in the way you feel a cold wind or the height of a cliff edge, you will never look at one of those diagrams the same way again. The Orion Arm is not small. The galaxy is simply that incomprehensibly large. Now let's talk about what the numbers actually say. The Orion Arm is estimated to be roughly 10,000 light-years in length. Some measurements place it slightly shorter. Others, particularly those drawing on more recent observational data, suggest it may extend considerably farther. But 10,000 light-years is the figure that has appeared in the scientific literature consistently enough to serve as a reliable working number. Its width runs approximately 3,000 to 3,500 light-years across. Those are the dimensions. A structure 10,000 light-years long and 3,500 light-years wide. And the first thing you need to do with those numbers is stop treating them like numbers and start treating them like distances. Because right now, your brain has almost certainly filed them away as large without actually processing what large means at this scale. 1 light-year is the distance light travels in a single year. Light moves at approximately 300,000 kilometers per second. Every second, it covers 300,000 kilometers. Every minute, roughly 18 million kilometers. Every hour, more than 1 billion kilometers. Every day, approximately 26 billion kilometers. And after a full year of traveling at that velocity, without slowing, without pausing, without deviation, light has covered approximately 9.46 trillion kilometers. That is 1 light-year. 1. A single unit on the scale we are discussing. Now consider the nearest star to our Sun, Proxima Centauri. It sits at a distance of 4.24 light-years. 4 light-years. At the speed of light, getting there takes just over 4 years. At the speed of the fastest spacecraft humanity has ever built, the Parker Solar Probe, at its peak velocity of roughly 192 kilometers per second, reaching Proxima Centauri would take approximately 73,000 years. 73,000 years of continuous travel, to reach the single nearest star, a journey begun at the time the first anatomically modern humans were painting animals on cave walls in Europe would not yet be complete. That is 4.24 light-years. The Orion Arm is 10,000. Let that ratio settle. 10,000 divided by 4 is roughly 2,500. The Orion Arm is about 2,500 times the distance from the Sun to its nearest stellar neighbor. If the journey to Proxima Centauri at our fastest speed takes 73,000 years, then crossing the Orion Arm at that same speed would take something in the range of 160 million years. 160 million years of continuous travel at the fastest velocity any human-made object has ever achieved. 160 million years ago, the first flowering plants had not yet appeared on Earth. The continents were arranged in configurations utterly unlike anything on a modern map. Dinosaurs had not yet reached their peak diversity. The entire span from those ancient seas to this present moment would pass twice over before you reach the other end of the structure we call home. And that is not travel to a distant galaxy. That is not a journey to another star system or even to the edge of the solar system. That is crossing the arm we already live inside, moving from one end of our own local galactic neighborhood to the other. Let us try the same calculation using light itself. If you sent a beam of light from one end of the Orion Arm toward the other, that beam would travel for 10,000 years before arriving. 10,000 years. Consider what that span of time means in human terms. 10,000 years ago, the agricultural revolution was just beginning. The first permanent human settlements were being established in river valleys across the Middle East. Stonehenge would not be constructed for another 5,000 years. The Great Pyramids of Egypt were still 8,000 years in the future. The entire recorded history of human civilization, every war, every empire, every invention, every philosophical tradition, every scientific discovery, every work of art, every generation of human beings born and lived and died since the first seeds were deliberately planted in cultivated soil, all of that fits within a span of approximately 10,000 years. If a beam of light had been fired across the Orion Arm at the moment the first human farmer knelt down and pressed a seed into the earth, it would be arriving at the far end right now, tonight, this moment. The entire lifespan of human civilization, measured in light travel time, is exactly the length of the arm we inhabit. And remember, nothing can actually travel at the speed of light. Light is not a vehicle, it is radiation. Mass cannot reach that speed. The 160 million year figure from earlier, using the fastest real spacecraft, is the honest number. The 10,000 year figure is the theoretical minimum, available only to something that has no mass at all and travels as pure electromagnetic energy. For anything physical, anything made of matter, the Orion Arm is not a destination. It is a dimension so vast that it effectively defines the boundary of what is reachable. The width is equally hard to hold in the mind. 3,500 light-years across, the short dimension, the narrow direction, the smaller of the two measurements. At the speed of light, crossing the width of the Orion Arm takes 3,500 years. That is roughly the span from the height of ancient Egypt's New Kingdom, the era of Ramesses the Great, to the present day. From the time Egyptian scribes were inscribing hieroglyphs onto stone temple walls to right now, this very evening, that is approximately how long it takes light to cross the width of the arm we live in. Now here is where something important happens, because these numbers, as staggering as they are in isolation, become even more disorienting when you place them next to the images your brain has been using to represent them. Those galaxy diagrams, the ones that show the Milky Way viewed from above, with the spiral arms color-coded and labeled, the ones you have seen in textbooks, on science websites, projected onto screens in school classrooms and planetarium domes. Those diagrams are typically displayed on an image somewhere between 20 and 40 centimeters across on a screen or printed page. The entire Milky Way, 100,000 light-years in diameter, fits within that space. On a 30-centimeter diagram, each centimeter represents approximately 3,300 light-years. The Orion Arm at 10,000 light-years occupies roughly 3 centimeters. 3 centimeters of ink on a page Its width of 3,500 light-years corresponds to just over 1 centimeter. 1 centimeter, the width of a fingernail. That is what the Orion Arm looks like on a galaxy diagram. A sliver of color about the width of your fingernail and about as long as the first joint of your thumb. Your brain looks at that sliver and draws a conclusion. It compares the sliver to the sweeping curves of the major arms, which on the same diagram might span 15 or 20 centimeters, and it renders a judgment. Small, minor, insignificant. That judgment happens automatically, without conscious deliberation, in the visual processing centers of your brain. It is the same mechanism that tells you a building in the distance is smaller than a tree in the foreground, even though the building is obviously larger. Your brain reads visual proportion and infers size. It is extraordinarily good at that task when the subject is something that exists at human scales. It is catastrophically wrong when the subject is a galaxy diagram, because every millimeter on that diagram represents hundreds of light-years of real physical space. Every fraction of a millimeter contains distances that no human technology could bridge in any civilizational timeframe. The diagram has taken something incomprehensibly vast and flattened it to the width of a fingernail, and your visual cortex has processed it the way it would process an actual fingernail-sized object. Something small, something you could pick up, something you could cross in a step. But you cannot cross the Orion Arm in a step. You cannot cross it in a lifetime. You cannot cross it in 1,000 lifetimes stacked end to end. The diagram and your brain have entered into an agreement that produces a completely false trenchant of scale, and that impression has been reinforcing itself every time you have encountered a galaxy map, for as long as you have been looking at them. Here is an analogy that might help feel the compression. Imagine a printed map of a large country, say the continental United States, which stretches approximately 4,500 kilometers from coast to coast. On a typical printed map of that country, the full width might span 25 centimeters across the page. Now suppose that somewhere on this map there is a geographic feature, a river valley, a mountain range, a region of some kind, that on the map appears to be about 1 centimeter wide. Your eye registers it and thinks, small, a minor feature. But 1 centimeter on that map represents 180 kilometers of actual terrain. 180 kilometers. That is a distance containing multiple cities, hundreds of towns, thousands of square kilometers of land, rivers, forests, roads, and millions of people. You could not walk across it in a week. You could not see from one side to the other on the clearest day. It is a vast and complex region of the real world, and the map has compressed it to something your thumb can cover. Now apply that logic to the galaxy diagram, except the compression is not a factor of 1800, it is a factor of roughly 30 trillion. Every centimeter of a galaxy diagram represents 3,300 light-years. 3,300 light-years, each one containing 9.46 trillion kilometers. The compression is so extreme that the concept of scale essentially dissolves. Your visual system was not designed to interpret images where a centimeter represents 31,000 trillion kilometers. It was designed to interpret images where a centimeter represents a centimeter. When you look at a galaxy diagram, you are asking a perceptual system built for one world to make sense of an image, encoding an entirely different order of magnitude. It cannot do it. It defaults to proportion. And proportion in this context is a lie. The Orion Arm is not the size your eye tells you it is on those diagrams. It is not proportionally smaller than the Perseus Arm, in the way a suburb is smaller than a city. It is absolutely enormous by any standard that has ever applied to anything in human experience. The Perseus Arm is larger, that is true, but the Orion Arm's relationship to the Perseus Arm is not the relationship between a pebble and a boulder. It is the relationship between one unimaginably large thing and another unimaginably large thing that happens to be somewhat larger. The difference between them is real, but both exist so far beyond the boundary of human intuitive comprehension that calling one small relative to the other produces a misleading impression. Think of it this way. Mount Everest is 8,849 meters tall, Mont Blanc, the highest peak in the Alps, is 4,807 meters tall. Mont Blanc is roughly half the height of Everest. If you showed someone those two mountains on a diagram scaled to the same image, Mont Blanc would look noticeably smaller. Proportionally it is. But would you call Mont Blanc a minor hill? Would you look at a 4,800-meter mountain and dismiss it as insignificant because there is a taller mountain elsewhere? Of course not. 4,800 meters is a mountain that kills experienced climbers, that generates its own weather systems, that towers above everything for hundreds of kilometers in every direction. Its relationship to Everest says nothing about whether it is, in any absolute sense, large. The Orion Arm is Mont Blanc in this comparison. Not the tallest peak, genuinely shorter than the major arms surrounding it, but still a structure of staggering absolute scale, containing dimensions and distances and volumes that reduce every human achievement in the realm of exploration to something invisible. Let us try one more frame of reference, because repetition from different angles is the only tool available when intuition has already exhausted its capacity. The speed of light again, 300,000 kilometers per second. In 1 second, a photon of light could circle the Earth more than 7 times. In 8 minutes and 20 seconds, it travels from the Sun to the Earth. In about 4 years, it reaches the nearest star. In about 2.5 million years, it reaches the Andromeda Galaxy, our nearest large galactic neighbor. And in 10,000 years, it crosses the Orion Arm. 10,000 years at 300,000 kilometers per second. That is how wide our local neighborhood is. That is the minimum transit time, achievable only by something with no mass, traveling at the universe's absolute speed limit.
This is an external galaxy,
For anything real, anything
In contrast,
physical,
our own
the
galaxy is
number
observed
is
from
so
within,
much
through
larger
obscuring dust and
that the
gas.
light speed figure almost seems reassuring by comparison, the way the distance to the horizon feels comforting compared to the distance to the moon. The actual crossing time at realistic velocities is not a journey, it is a geological epoch. And yet this is the structure that sits between two lines on a textbook diagram. This is the feature your eye skips over on its way to the more impressive-looking arms. This is the thing that generations of students have absorbed as minor, as a spur, as secondary, as a footnote in the galaxy's architecture. Not because anyone intended to mislead them, but because no diagram, no matter how carefully constructed, can communicate the true scale of a structure this large on a medium this small. The information loss is total. What survives the compression is proportion, not magnitude. And proportion without magnitude is the source of every false impression you have ever had about the Orion Arm. What diagrams show you is where the Orion Arm sits relative to other features. What they cannot show you is how large it is in any absolute sense. Those are two entirely different things, and only one of them matters for understanding what the Orion Arm actually is. You have been shown the first your entire life. Tonight, you are finally seeing the second. The Orion Arm is 10,000 light-years long. That is the truth behind the diagram. That is the reality those 3 centimeters of ink are trying and failing to represent. And now that you have some sense of what that distance means in human time, in spacecraft travel time, in the history of civilization, in the language of light itself, it is time to look at what is actually inside that distance. Because the Orion Arm is not empty. It is not a quiet corridor between two livelier structures. It is full, rich, complex, spectacular, and the objects inside it include some of the most famous and breathtaking things that have ever been observed in the night sky. Every star you have ever seen with your naked eye is inside the Orion Arm. Every single one, not most of them, not the majority, all of them. The entire visible night sky, every point of light your eyes can resolve on the clearest, darkest night, every constellation humans have traced and named and told stories about across thousands of years of civilization, every star that has ever guided a navigator across an ocean or inspired a poet or caused a child to point upward and ask what it was. All of it lies within the boundaries of this one structure. The Orion Arm contains our entire observable stellar neighborhood and then extends thousands of light years beyond the farthest star your eyes could ever detect unaided. This is not a coincidence. It is a consequence of scale. The Orion Arm is our home region of the galaxy. and the stars visible to the naked eye are, by cosmic standards, extremely nearby. The farthest star typically visible without optical assistance under ideal conditions is somewhere around 4,000 light-years away. That is less than halfway across the Orion Arm's length. Everything your eyes can see of the night sky sits within roughly the inner half of the structure we live in. The outer half, the more distant regions of the arm, the star-forming complexes thousands of light-years away, the stellar populations near the arm's far edge, all of it lies beyond unaided human perception, accessible only through telescopes, and the patient accumulation of data over decades of observation. But the arm does not just contain the stars your eyes can reach. It contains some of the most remarkable objects in the entire galaxy. Consider the Orion Nebula. If you have ever seen an astronomy photograph that moved you, a glowing cloud of rose and violet gas lit from within by the fierce radiation of newborn stars, there is a reasonable chance it was this object. The Orion Nebula is one of the most photographed targets in all of astronomy, visible to the naked eye on a dark, clear night as a faint smudge in the sword of the constellation Orion below the three-star belt. It sits approximately 1,340 light-years from Earth, comfortably within the Orion Arm. The nebula itself spans roughly 24 light-years across. 24 light-years, a single cloud of gas and dust 24 light-years in extent, and it is one object among many within our arm. Inside the Orion Nebula, the process of stellar birth is happening right now, not metaphorically, not in some distant future tense. Right now, at this moment, as you sit reading these words, clouds of hydrogen gas within that nebula are contracting under the force of their own gravity. Denser pockets within those clouds are pulling in surrounding material, growing more massive, heating up as gravitational energy converts to thermal energy. Some of those contracting cores have already crossed the threshold and ignited nuclear fusion in their interiors. Stars have been born there within the last million years, which by astronomical standards means recently. Others are still in the process of forming, surrounded by rotating disks of gas and dust that will, over the next several million years, coalesce into planets. Future solar systems are assembling themselves inside the Orion Nebula as you exist. Worlds that do not yet exist are in the process of being built inside this one object, inside this one arm. The Orion Nebula is extraordinary, but it is not alone. The Cygnus star-forming complex is another vast region of active stellar birth within the Orion Arm, located roughly 4,000 to 5,000 light-years from Earth in the direction of the constellation Cygnus. This complex is one of the most productive stellar nurseries in our region of the galaxy. It contains enormous molecular clouds, sweeping filaments of cold gas, and several massive stellar associations, including the Cygnus OB2 Association, which harbors thousands of young stars, among them some of the most massive and luminous objects known in the Milky Way. These are stars dozens of times more massive than the Sun, burning at temperatures so extreme that they shine millions of times brighter. They are profligate with their energy, spending their enormous fuel reserves at rates that would exhaust a Sun-like star in a fraction of its normal lifetime. Where a star like our Sun burns steadily for 10 billion years, these giants may exhaust themselves in a few million, then detonate in catastrophic supernova explosions that briefly outshine entire galaxies. The Cygnus complex is a powerhouse, a place of extraordinary stellar violence and creativity happening simultaneously, thousands of light years away, entirely within the arm we call home. Betelgeuse is inside the Orion Arm. That name is almost certainly familiar to you. The bright orange-red star marking the shoulder of the constellation Orion, one of the most recognizable points of light in the winter sky across the northern hemisphere. Betelgeuse sits somewhere between 500 and 700 light-years from Earth, a range that reflects genuine measurement uncertainty, because pinning down the precise distance to a star that is actively pulsating, expanding and contracting over cycles of hundreds of days is genuinely difficult, even with modern instruments. What is certain is that Betelgeuse is a red supergiant, a star in the advanced stages of its life, and it is almost incomprehensibly large. If you placed Betelgeuse at the center of our solar system, where the Sun currently sits, its outer atmosphere would engulf Mercury, Venus, Earth, and Mars. It would extend past the orbit of Jupiter. Some estimates suggest it might reach beyond Jupiter entirely.
This is an
a single star so enormous that our entire inner solar system would be submerged within it. Betelgeuse is dying, not on a human timescale, and not necessarily soon by astronomical standards, but it is in the late stages of stellar evolution, and at some point it will undergo a core collapse and explode as a supernova. When that happens, it will become briefly visible in Earth's daytime sky. It will shine with something approaching the brightness of the full moon, visible even when the sun is above the horizon, a second light source competing with daylight. The explosion could happen within the next 100,000 years, or it could happen tomorrow. We do not know. The uncertainty is genuine, but whenever it occurs, it will be an event inside the Orion Arm, one of our stellar neighbors, concluding its life in a burst of energy that will briefly rival the output of 100 billion ordinary stars. The Crab Nebula is inside the Orion Arm. This object is the remnant of a stellar explosion that was observed and recorded by Chinese astronomers in the year 1054. They documented a new star appearing in the sky, so bright that it was visible during daylight hours for 23 consecutive days, and remained visible to the naked eye at night for nearly 2 years before fading. What they were witnessing was a massive star, approximately 6,500 light-years away, tearing itself apart at the end of its life. The explosion itself had actually occurred 6,500 years earlier. The light from the detonation had spent 65 centuries crossing the Orion Arm before it finally reached Earth, and was seen by those astronomers in the 11th century. What remains at that location today is a rapidly expanding cloud of superheated gas and debris, approximately 11 light-years across, still growing outward from the point of the original explosion, and at its center, a pulsar, a rapidly spinning neutron star, the collapsed remnant of the original stellar core, rotating approximately 30 times per second, and sweeping beams of radiation through space, like the beam of a lighthouse rotating at 30 revolutions per second. The Crab Nebula has been studied intensively for decades and continues to yield new insights into the physics of extreme environments. It is one of the most scientifically productive objects in the observable sky, and it is inside our arm. The Veil Nebula is inside the Orion Arm. This is the gossamer remnant of a star that exploded approximately 11,000 years ago at a distance of roughly 800 light-years from Earth. When it detonated, it would have been strikingly bright in the sky, outshining everything except the sun and moon, visible to the humans alive at that time, though no written record of it survives, because writing had not yet been invented. What remains today is an enormous, delicate shell of expanding gas, roughly 100 light-years across, glowing with the energy still propagating outward from that ancient explosion. In long-exposure photographs, the Veil Nebula appears as a series of luminous filaments and wisps, thin curving threads of ionized gas that look almost translucent against the background stars. It is one of the visually beautiful consequences of stellar death, all of it contained within the Orion Arm. The Gaia Nebula is inside the Orion Arm. This is one of the largest emission nebulae in the sky,
built after the
as seen from Earth,
1572
spanning
supernova,
approximately 36 degrees of the celestial sphere. For reference, the full moon subtends about half a degree. The Gaia Nebula covers an area of sky 70 times the diameter of the full moon. It sits roughly 1,500 light-years away and extends for approximately 1,000 light-years in actual physical size. A single nebula inside the Orion Arm that is itself 1,000 light-years across. The Pleiades star cluster is inside the Orion Arm, those 7 bright blue stars clustered together in the constellation Taurus, visible on winter evenings and recognized by virtually every culture in human history as a distinct and significant grouping, sit approximately 440 light-years from Earth. They are young stars, formed together from the same molecular cloud, roughly 100 million years ago, still loosely bound by mutual gravity still embedded in wisps of the gas and dust from which they formed. The Hyades cluster, the nearest open cluster to Earth at approximately 150 light-years, is inside the Orion Arm. The California Nebula is inside the Orion Arm. The Rosette Nebula is inside the Orion Arm. The Lagoon Nebula, sitting at the near edge of the Sagittarius Arm, but visible from within ours, is close enough to blur the boundary. These are the named objects, the celebrated landmarks that appear in astronomy textbooks and observatory images and popular science articles, but the Orion Arm contains vastly more than its famous features. It contains the ordinary population of stars that makes up the bulk of its mass and volume. Red dwarf stars, the most common type in the galaxy, dim and cool and extraordinarily long-lived, burning their modest fuel supplies so slowly that they will still be shining trillions of years from now, long after the sun has exhausted itself and faded. Yellow dwarfs like our sun, middle-aged and stable, converting hydrogen to helium in their cores at a measured pace. Orange dwarf stars somewhat cooler and smaller than the sun. White dwarfs, the dense remnants of sun-like stars that have already completed their lives and shed their outer layers, now cooling slowly over billions of years. Binary star systems, where two stars orbit their common center of mass, some of them close enough that one draws material from the surface of the other. Triple and quadruple systems bound in complex gravitational arrangements. Planetary nebulae, the expanding shells of gas ejected by dying sun-like stars in their final stages, glowing with energy as the ultraviolet radiation of the cooling stellar core ionizes the escaping material. All of this is inside the Orion Arm, billions of stars in every stage of existence, from newly ignited protostars still embedded in the clouds that birthed them to ancient stellar remnants that have been cooling in darkness for billions of years. And then there are the planets. Before the late 20th century, the existence of planets around other stars was theoretical. We had compelling reasons to believe they should exist, based on our understanding of how stars form, but we had no direct evidence. The first confirmed detection of a planet orbiting a sun-like star came in 1995, when astronomers Michel Mayor and Didier Queloz, working with the Elodie spectrograph at the Haute-Provence Observatory in France, detected a Jupiter-sized world orbiting a star called 51 Pegasi, about 50 light-years from Earth. That discovery, which would eventually earn them the Nobel Prize in Physics in 2019, opened a door that has never closed. What followed over the next 3 decades was a systematic revelation about how common planets are throughout the galaxy. NASA's Kepler Space Telescope, launched in 2009 and operational until 2018, was designed specifically to measure the frequency of planets around other stars by staring continuously at a single patch of sky containing over 150,000 stars and watching for the tiny, periodic dimmings that occur when a planet passes in front of its host star. These transits, as they are called, cause the star's brightness to drop by a fraction of a percent, sometimes less than 1/100%, for a period of hours. Detecting them reliably requires extraordinary precision and the kind of patient, unblinking observation that only a space-based instrument can provide. What Kepler found transformed the field permanently. Planets are not rare, they are not occasional. They are not special exceptions to some general rule of stellar solitude. They are everywhere. The data showed that on average, every star in the Milky Way hosts at least one planet. Many stars host multiple planets. Rocky worlds roughly the size of Earth turned out to be remarkably common, far more common than optimistic pre-mission estimates had suggested. The galaxy is not a collection of isolated stars burning alone in empty space. It is a collection of solar systems, each one a complex arrangement of worlds orbiting a central star, each one potentially harboring its own geology, its own chemistry, its own history. Kepler's successor mission, the Transiting Exoplanet Survey Satellite, known as TESS, launched in 2018 and has continued expanding our catalogue of known worlds around nearby stars, confirming and extending the statistical picture Kepler established. The James Webb Space Telescope, operational since 2022, has added the ability to analyze the atmospheres of some of these worlds, detecting the chemical signatures of the gases surrounding them. The inventory of known exoplanets now numbers in the thousands, with statistical models suggesting the true total runs into the billions across the galaxy. Apply those occurrence rates to the Orion Arm. If the arm contains several billion stars and the average star hosts at least one planet, then the arm contains at least several billion planets. But the average is not one. Kepler's data indicates something closer to 1.5 to 2 planets per star, when all types of planetary systems are accounted for. That pushes the total number of worlds within the Orion Arm toward 10 billion. 10 billion individual worlds, each one a distinct physical environment, circling its own star, subject to its own forces and processes, existing in its own particular corner of this one structure. Among those 10 billion worlds, a significant fraction are rocky. Some fraction of those rocky worlds orbit within their star's habitable zone, the range of orbital distances where temperatures could permit liquid water to exist on the surface. For Sun-like stars, roughly 1 in 5 may host a rocky planet in the habitable zone. For red dwarf stars, which are far more numerous than Sun-like stars, the fraction may be comparable or even higher. Though the nature of habitable conditions around a red dwarf is more complex due to stellar activity and tidal locking. Conservatively, the Orion Arm likely contains hundreds of millions of rocky planets in habitable zones. Hundreds of millions of worlds where, under at least some circumstances, the surface conditions might support liquid water. Whether any of them harbor life is a question we cannot answer. It may be the most important unanswered question in the history of science. But the physical conditions that seem prerequisite for life, as we understand it, liquid water, chemical complexity, a stable energy source, a rocky surface. These conditions are not rare inside the Orion Arm. They are abundant, scattered across hundreds of millions of worlds distributed throughout 10,000 light-years of space. All of them unknown, all of them unexplored, all of them unnamed. Every single one sitting in darkness we have never
Built after the
illuminated,
1572
on worlds we have never
supernova,
seen,
Uranoborg
and star
upon
systems we
missed
have at
red.
best detected as faint periodic
De Nova
dimmings
Stella,
in the light
the
of their
work that gave
host
us the word
stars.
nova,
The Orion
began the
Arm
modern
contains more
understanding of
worlds
stellar
than
chain.
humanity could
Behold
visit
the
if we
supernova of
launched a new
1604.
interstellar
This
mission
shatters the
every
immutable
single
spheres of
day
outer star.
for the
A new
entire
truth
remaining
emerges.
lifespan of the Sun.
Kepler
We
observed
would not make a
1604
dent.
supernova.
We would not come
The
close.
telescope arrived,
We would
but too late
explore
to
an
witness it.
imperceptible fraction and never reach the boundary of what the arm contains. And all of this, every nebula
late
and
2019,
supernova remnant
Betelgeuse
and
worldwide
stellar
stars
nursery and
mysteriously
planetary
drank by
system
early
and
2020.
molecular
Betelgeuse
cloud
started
and
its slow
stellar
recovery.
remnant and open cluster and binary pair, every famous object and every anonymous star and every unnamed world fits inside 3 centimeters of ink on a textbook diagram. 3 centimeters that your eye crosses in a fraction of a second. 3 centimeters that your brain files as minor. 3 centimeters that contain 10 billion worlds and billions of suns and the most spectacular objects in the observable night sky, and more distance than any physical object has ever traversed or will ever traverse within the span of human civilization. That is what the Orion Arm contains. Not emptiness, not a quiet corridor, life, in all its stellar and planetary and possibly biological variety, distributed across a volume of space so vast that the fastest thing in the universe needs 10,000 years to traverse it, and we are inside it. We are part of it. We are, in the most literal possible sense, made of it. The carbon in your cells was forged in the core of a star that lived and died somewhere in this arm before the Sun existed. The oxygen in your lungs was synthesized in a stellar interior and scattered into the interstellar medium by a supernova explosion that happened within these boundaries. The iron in your blood was produced in the violent death of a massive star somewhere in this structure, millions of years before the solar system formed, drifting through the gas and dust of the Orion Arm until gravity gathered it into the cloud that collapsed to become everything we are. You are not observing the Orion Arm from outside. You are not a spectator of it. You are composed of it. You are a temporary and extraordinarily improbable arrangement of atoms that originated in this arm's stellar furnaces, organized by 4 billion years of biological evolution, into something capable of looking out at the rest of the arm and asking what it is. The arm is not out there. The arm is here. The arm is you, looking at itself. And this is still only the near part, the local region, the familiar corner. There is an entire architecture of structure within the Orion Arm itself, neighborhoods within neighborhoods, environments shaped by ancient stellar explosions, bubbles of hot gas carved into the cold interstellar medium, star-forming regions triggered by the deaths of earlier generations of stars. The Orion Arm has an interior landscape as complex and layered as anything visible from the outside. And to understand that landscape, you first need to understand the strange and ancient cavity we are floating inside right now. We are floating inside a bubble. Not metaphorically, not as a poetic device. Literally, the Sun and its entire family of planets, every world in our solar system, every moon, every asteroid, every comet drifting in the cold outer reaches of the Oort cloud, all of it sits inside a vast cavity in the interstellar medium, a region of space where the gas between the stars is far thinner and far hotter than the surrounding material of the Orion Arm. This cavity is called the local bubble, and it has been shaping the environment around our solar system for millions of years without most people ever knowing it exists. The local bubble is roughly 1,000 light years across, though its shape is not a clean sphere. It is irregular, lumpy, elongated in some directions and compressed in others, more like a vast misshapen hollow in the interstellar gas than a geometrically precise void.
Only its radio and X-ray emissions
is filled with extremely tenuous,
revealing the
extremely
explosion
hot
decades
plasma,
later.
gas that has been heated to temperatures of millions of degrees, but spread so thin that it contains almost nothing in terms of actual mass. The walls surrounding this interior are denser than the interior itself.
This is an external
compressed
galaxy,
shells of
seen cleanly
gas
from
and
outside.
dust,
In
pushed
contrast,
outward
our own
by the
galaxy
same
is observed from
forces
within
that created the
through obscuring dust and
cavity.
gas.
How did it form? The answer is violence. Ancient, distant, and now silent violence, but violence nonetheless. Somewhere between 10 and 15 million years ago, a series of massive stars in our region of the Orion Arm reached the ends of their short and prodigal lives and exploded. Not one explosion. A sequence of them spread over millions of years, each one releasing an enormous pulse of energy into the surrounding interstellar medium. These were not distant events on the far side of the arm. They happened close enough, in galactic terms, that their combined shock waves propagated outward through the gas surrounding our current location, sweeping material ahead of them, compressing it into a dense shell, and leaving behind a hot, low-density cavity. The Sun did not cause this. The Sun is a middle-aged, thoroughly ordinary yellow dwarf star that has been burning steadily for 4.5 billion years and will continue doing so for approximately another 5 billion. It has never exploded and will never explode in the dramatic fashion of a massive supernova. But the Sun drifted into the local bubble sometime in the last few million years, and it has been traveling through this cavity ever since, along with all of its planets, all of us among them. We are passengers inside a structure carved by stars that died before our ancestors existed. The bubble we inhabit was blown by stellar explosions that occurred when the ancestors of modern humans were still sharing the African savanna with other hominin species. By the time the first stone tools were being shaped, the local bubble was already ancient. By the time the first cities were being built, the shock waves from those founding supernovae had long since faded into the general structure of the interstellar medium. What remains today is the hollow they left behind, and we are floating in the middle of it. The interior of the local bubble is not empty of stars. Thousands of stars exist within it, including the Sun and all of our nearest stellar neighbors. Proxima Centauri is inside the local bubble. Alpha Centauri is inside the local bubble. Sirius, the brightest star in the night sky at a distance of 8.6 light-years, is inside the local bubble. Essentially, every star you have ever seen with the naked eye on a clear night, at least the nearby ones, the ones within a few hundred light-years, is inside this same cavity. Our immediate stellar neighborhood, the familiar stars that define the constellations and have guided human navigation for millennia, all of it sits within this ancient bubble carved by long-dead stars. What the local bubble reveals is something important about the Orion Arm's internal structure. The arm is not uniform. It is not a smooth, homogeneous distribution of gas and stars spread evenly across 10,000 light-years. It is textured, layered, complex, shaped at every scale by the accumulated consequences of billions of years of stellar birth and death. Stars form from dense clouds of gas. They live their lives radiating energy outward into the surrounding medium.
East Asian
They
astronomers
die,
observed a bright guest
sometimes
star in
gently,
Cassiopeia,
shedding
linking
their
it to the
outer
modern
layers
nebula
and expanding shells, sometimes violently, detonating in supernovae that compress and heat and sculpt the surrounding space. Each generation of stars reshapes the environment for the next.
Built after
The
the
interstellar medium is
1572
not a static
supernova,
background.
Uranoborg
It is a
on Pond
dynamic,
Mishpren.
evolving landscape, constantly
Nova
being
Stella, the
reworked
work
by
that
the
gave us the word
objects
nova
embedded within
and
it.
began the
The
modern
local
understanding of
bubble
stellar
is one
change.
feature of this landscape, but the Orion Arm contains countless others, shells of compressed gas surrounding regions
observed
where
the
massive
16.4
stars have
supernova.
blown powerful
Telescope
stellar winds
arrived,
for
but
millions
too
of
late to
years.
witness it.
Cavities similar to the local bubble but of different sizes and ages, some younger and more energetic,
In late
others older
2019,
and more
Betelgeuse
diffuse,
worldwide charts
their boundaries
mysteriously dipped. By
merging
early
and
2020,
overlapping in
Betelgeuse started
complex
its slow
three-dimensional
recovery.
arrangements. Filaments of cold, dense gas stretching for hundreds of light years, marking the edges of ancient shock waves, molecular clouds, cold and dark, containing enough mass to form thousands of stars, drifting slowly through the arm, waiting for some gravitational disturbance to trigger their collapse. In 2022, a research team using data from the European Space Agency's Gaia spacecraft published a study that illuminated the local bubble's role in our immediate stellar neighborhood with unprecedented clarity. Their analysis showed that virtually every active star-forming region within roughly 1,000 light-years of the Sun sits on the surface of the local bubble, along its compressed outer walls, not in its interior. The implication was striking. The star formation we observe in our immediate neighborhood, the stellar nurseries that have been producing new suns in our vicinity over the last few million years, was triggered by the local bubble itself. The supernovae that carved the cavity pushed gas outward into the walls. The compressed gas in those walls became dense enough to begin gravitational collapse. New stars formed from the remnants of the explosions that cleared the interior. Death-feeding creation. The supernova explosions that cleared our local region of dense interstellar gas simultaneously seeded the conditions for new stellar birth along the cavity's expanding boundary. We are the indirect beneficiaries of stellar catastrophes that happened millions of years ago, living inside the hollow they created, surrounded at our neighborhood's edge by young stars born from material those explosions compressed. This kind of layered causality operates throughout the Orion Arm at every scale. It is not unique to our local region. It is the fundamental mechanism by which spiral arms renew themselves, by which one generation of stars creates the conditions for the next, by which the arm maintains its character as a region of ongoing stellar activity across billions of years of galactic history. Now, let us do something that the local bubble makes possible. Let us zoom outward from our position in a series of deliberate steps, expanding our sphere of consideration in stages, and observe how the Orion Arm reveals itself at increasing distances, not as an abstraction, as a physical landscape, with structure and depth and character at every scale. Begin close, very close. Within 15 light-years of the Sun, astronomers have catalogued approximately 50 known star systems. This is a sphere 30 light-years in diameter, centered on our solar system, containing 50 individual suns or gravitationally bound groups of suns. Some of them are single stars. Some are binary pairs orbiting their shared center of mass. A few are triple systems. The names of the closest are familiar to anyone who has spent time with astronomy. Proxima Centauri at 4.24 light-years. Alpha Centauri A and B, the binary pair that Proxima orbits at a slightly greater distance of 4.37 light-years. Barnard's star at 6 light-years, a dim red dwarf moving through space faster than any other known star relative to the Sun. Wolf 359 at 7.9 light-years. Lalande 21185 at 8.3. Sirius at 8.6, the brightest star in the sky, not because it is intrinsically the most luminous, but because it is relatively nearby and genuinely brighter than average. These are our immediate neighbors, the stars right next door. And even this sphere, this 30 light-year bubble that represents our closest stellar community, is so large that reaching any of these stars with technology we
This is an
currently
external
possess
galaxy, seen
is
cleanly from
effectively
outside.
impossible
In contrast,
on any
our own galaxy is
civilizational
observed from within
timescale.
through obscuring dust and
Voyager
gas.
1, the most distant human-made object ever launched, has been traveling continuously since 1977. It is now approximately 24 light-hours from the Sun. 24 light-hours. The nearest star is 4.24 light-years away. 1 light-year contains approximately 8,760 light-hours. Voyager 1 has covered roughly 1/1,400th of the distance to Proxima Centauri in nearly 50 years of travel. At that rate, it would need roughly 73,000 years to reach the nearest star, if it were traveling in that direction, which it is not. Our entire sphere of physical exploration, the volume of space through which human-made objects have actually traveled, is approximately 24 light-hours in radius. Our immediate stellar neighborhood extends 15 light-years in every direction. The ratio between what we have physically reached and what constitutes our nearest community of stars is roughly 1 to 5,000. We have explored 1/5000th of the distance to our nearest neighbors. 1/5000th. Expand the sphere. 100 light-years from the Sun. Now the sphere is 200 light-years in diameter, and it contains roughly 14,000 known star systems. 14,000 individual suns within this volume, many of them familiar by name from the night sky. Arcturus, the bright orange giant in the constellation Boötes, sits about 37 light-years away.
It's sent the Crab
Vega,
pulsar.
the brilliant
Its
blue-white
beams
star
connect
that
that
marks
ancient
one
event to the
corner
living
of the summer
remnant today.
triangle, sits about
you saw it in
25
Cassiopeia.
light-years away. Capella, the bright
It is a
yellow
star,
giant in
confirm it.
Auriga, at 43 light-years. Fomalhaut, one of the first stars around which a debris disk suggestive of planet formation was imaged, at about 25 light-years. 14,000 star systems within a sphere whose radius is 100 light-years. And 100 light-years is 1% of the Orion Arm's length. We have expanded our view to encompass 14,000 stars, a volume that light takes a century to cross in any direction, and we have covered 1% of the arm we inhabit. Expand again. 500 light-years. The sphere is now 1,000 light-years in diameter, and the number of stars within it climbs into the hundreds of thousands. The volume is now large enough to contain genuine diversity in the stellar population. Within 500 light-years, you
February
encounter stars at
1987.
every stage of their life cycle.
massively dark,
Protostars still
for new era
embedded in their birth
astrophysics.
clouds, glowing in infrared, but not yet visible at optical wavelengths, as their cores heat toward the ignition temperature of nuclear fusion. Young, hot blue stars only a few million years old, burning fiercely through their hydrogen fuel. Middle-aged yellow and orange stars like the Sun, billions of years old and billions of years from their end. Old red giants that have exhausted the hydrogen in their cores and expanded to hundreds of times their original diameter as they process helium and heavier
Southwestern
elements in their outer
Petroglyph
shells.
star,
White dwarfs,
aligned with the
the
infrared
cooling
strong
remnants of
Perseus.
stars that have already
In
completed their
1181,
evolution
East Asian
and shed
astronomers
their
observed
outer
a bright
layers,
guest star in
now slowly
Cassiopeia, linking it
radiating
to the
away their
modern nebula
stored thermal energy into the surrounding darkness. Within 500 light-years, the sky becomes genuinely complex.
My lord,
Open
the guest
clusters
star
of young
blazes brighter
stars,
than Jupiter,
born
heaven's
together from the
commander
same
village in the
molecular
eastern sky
cloud
near Zeta
and
Tauri.
still moving
Built
through
after the
space as a loose
1572
gravitational
supernova,
family.
Uranoborg
Planetary
upon
nebulae, the glowing
Medjugorje.
shells of ionized gas ejected
Nova
by
Stella,
dying
the
sun-like
work that gave us
stars,
the word
each
nova
one marking
and
the
began the
conclusion
modern
of a stellar
understanding of
life.
stellar change.
Binary
Behold the
systems of
supernova
every
of
variety,
1604.
pairs
This
of
shatters the
stars
immutable
locked in
spheres of
orbital
Aristotle.
embraces
A
that
new
may have
truth
lasted for
emerges.
billions of years,
Kepler observed the
and
1604
everywhere,
supernova. The
planets,
telescope arrived,
worlds of every
but too late
size
to
and
witness it.
composition orbiting their parent stars in arrangements as varied as the stars themselves. 500 light-years is
In late
5% of the
2019,
Orion Arm's
Betelgeuse
length.
worldwide charts
We have covered
mysteriously dipped by early
5%,
2020.
and we
Betelgeuse
already
started
have
its slow
more
recovery.
astronomical richness than any human lifetime could catalogue, more individual worlds than human civilization has named objects of any kind throughout all of its history. Now pause at a particular scale, roughly 1,000 light-years, because this is approximately the scale of the local bubble, and at this distance something interesting happens. You begin to reach the bubble's outer walls. You begin to encounter the compressed shell of gas that marks the boundary between the hot, thin interior we inhabit and the denser material of the broader Orion Arm beyond. The transition is not sharp. There is no clear line where the bubble ends and the arm begins. But the density of interstellar gas increases as you move outward from the center, and the character of the environment changes. Inside the bubble, the interstellar medium is sparse and hot. Outside the bubble walls, it is denser, colder, more molecular. The conditions for star formation are more readily met in the denser outer regions, which is precisely why so many nearby star-forming regions cluster along the bubble's surface. At 1,000 light-years, you are beginning to reach objects that represent genuine landmarks of the Orion Arm's near interior. The Orion Nebula, at 1,340 light-years, sits just beyond the boundary of this sphere. The Orion Molecular Cloud, the enormous cold gas complex of which the Orion Nebula is merely the most luminous and visible component, extends across several hundred light-years and encompasses multiple star-forming regions in the same general area of the sky. The Perseus Molecular Cloud, another active stellar nursery, sits at roughly 1,000 light-years. The Taurus Molecular Cloud, one of the nearest regions of active low-mass star formation to the Sun, lies at about 440 light-years, well within this volume. 1,000 light-years is 10% of the Orion Arm, one-tenth. A sphere 1,000 light-years in radius centered on the Sun contains all of this. Tens of thousands of named stars, hundreds of thousands of unnamed ones, the entire visible night sky, and much beyond it, the local bubble and its walls, multiple active star-forming regions, ancient supernova remnants, open clusters, and planetary nebulae and binary systems in their thousands. All of that extraordinary complexity and richness, and it is 1/10 of the arm. Expand to 2,000 light-years. The sphere is now 4,000 light-years in diameter. The star count climbs into the billions. We are now deep enough into the Orion Arm to encompass some of its most famous and spectacular contents. At roughly 1,300 light-years, the Orion Nebula is now well inside the sphere. The Great Orion Molecular Cloud Complex, arguably the most studied region of star formation in the entire galaxy, is fully contained within our volume. Various stellar associations, loose groups of young stars that formed from the same general molecular cloud but have since dispersed somewhat, are included. Supernovae remnants from explosions that occurred within the last few tens of thousands of years, their expanding shells still propagating outward through the interstellar medium, are scattered throughout this volume. 2,000 light-years is 20% of the Orion Arm, 1/5. And the complexity of what sits within it is already beyond comprehensive human cataloguing. The Gaia spacecraft, which has measured positions and distances for nearly 2 billion stars across the Milky Way, has provided unprecedented detail on the stellar populations within this volume. Its data has revealed structures within the Orion Arm's near interior that were previously unmapped.
This is an external
elongated
galaxy, cleanly
chains
from
of young
outside.
stars
In
called
contrast, our
stellar
own galaxy is
strings,
observed from within, through
nested
obscuring
shells
dust
of
and gas.
compressed gas surrounding the local bubble and other nearby cavities, the three-dimensional architecture of molecular clouds, and their relationships to the star-forming regions embedded within them. 5,000 light-years, half the length of the Orion Arm in the traditional estimate. A sphere 5,000 light-years in radius centered on the Sun now encompasses what might reasonably be called the heart of our local galactic neighborhood. The star count within this volume is measured in the billions. The Cygnus star-forming complex, 4,000 to 5,000 light-years away, sits near the edge of this sphere. Supernova remnants from explosions that occurred thousands of years ago are distributed throughout the volume, their expanding shock waves still interacting with the surrounding interstellar medium, compressing gas, triggering star formation, injecting energy into the galactic ecosystem. Molecular clouds of every size, from small, dense cores actively forming single star systems to enormous complexes spanning hundreds of light-years, are scattered across the volume. Within 5,000 light-years of the Sun, you have more worlds than all of human history has given names to anything, more stars than all the grains of sand on all the beaches of all the continents of Earth combined, more distance in any direction than any physical object humanity has ever built could traverse in millions of years. And you have covered half the Orion Arm. The other half lies beyond, extending outward to the arm's far edge. containing its own
It sent the crab
star-forming
pulsar.
regions and stellar
Its beams
populations
connect
and
that ancient
supernova
event
remnants
to the
and
living
worlds,
remnant today.
all of it belonging to
Look,
the same
it's Star in
structure,
Cassiopeia.
all of it part of the same density wave,
It is a
the
star,
same
confirm
spiral
it.
feature, the same minor spur that textbooks mark with a thin line and a small label. And here is what makes this accumulation
holes
of
in
scale
space.
genuinely
Mark the
difficult to absorb.
Recorded
At no
15
point in this
degrees, 23
outward
minutes.
journey, at 15 light years, at 100, at 500, at 1,000, at 5,000, does the
A new star in the
complexity or the
heavens, brilliant
richness
and fixed
or the
enough
sheer
lucas.
quantity
I must
of what
record
is
this
contained
celestial
within the
marvel.
expanding sphere ever diminish. It only grows. Every step outward reveals more structure, more objects, more distance, more worlds. The Orion Arm does not thin out as you explore it. It deepens. It reveals new layers of organization and new populations of
SN
objects at every scale of
1987A,
examination.
the closest
This is
supernova.
what lives
Its
inside
ring of
those
shock
3
gas
centimeters
continues
on
to
a
grow.
textbook
February
diagram.
1987.
Not emptiness punctuated by a
massive
few
dart
notable
for
objects.
new era in
An
astrophysics.
entire layered universe of structure. From the 1,000 light-year bubble we float inside to the billions of stars distributed across 10,000 light-years of space. Each layer revealing new complexity, each scale of examination uncovering new populations of objects that no previous scale had shown. The Orion Arm is not a simple feature. It is not a uniform expanse. It is a landscape. A vast, intricate, ancient landscape of matter and energy, shaped by billions of
Southwestern
years of stellar
Petrojurassic
activity,
star,
organized by
aligned with the
gravity and
infest
density
closer.
waves, and the
In
cycling of
1181,
generations of
East Asian
stars,
astronomers observed a
filled
bright
with
guest star
worlds
in
we have never
Cassiopeia,
seen and
linking it to the
distances we
modern
cannot
nebula
cross,
Pie.
and structures we are only now beginning to map with the precision they deserve. And our ability to map it has
My lord,
changed
the guest star
dramatically in
blazes
recent
brighter than
years,
Jupiter for heaven's
because a
command ability.
spacecraft
In the
launched
eastern
from
sky
Earth in
near Centauri.
2013
Built after
began
the
returning data that
1572
has fundamentally
supernova,
revised
Uranophore
everything we thought
Gampon
we knew
Mist
about the
Brent.
Orion Arm's true extent, its
De Nova
actual
Stella,
dimensions,
the work that
and
gave
its
us the
proper
word
place
nova,
in the
and
galaxy's
began the modern
architecture.
understanding of
For most
stellar
of the
change.
20th
Behold the
century,
supernova
our
of
picture of the
1604.
Milky Way's
This shatters
spiral
the immutable
structure
spheres of
was
Aristotle.
built from
A new
inference,
truth emerges.
from indirect
Kepler
measurements,
observed the
from
1604
methods that were
supernova.
ingenious and
Telescope
carefully
arrived, but too
constructed
late to
and
witness it.
genuinely productive, but that carried uncertainties large enough to blur the details of structures thousands of light years away.
In late 2019,
We knew the
Betelgeuse
broad
worldwide
outlines.
charts mysteriously
We knew
dipped.
there
By
were
early
spiral
2020,
arms.
Betelgeuse
We
started
knew
its slow
roughly where
recovery.
some of them were. But the precise dimensions of individual features, the true extent of the Orion Arm, the exact arrangement of its boundaries, the full account of its stellar populations, all of that remained frustratingly unclear. Not because astronomers were not trying, because the tools available were not equal to the task. The fundamental problem is the one we have already discussed. We are inside the galaxy. We are trying to map, and mapping something from the inside without the ability to step outside and look down at the whole structure requires workarounds. Clever, painstaking, carefully validated workarounds that get you closer to the truth but never quite arrive there without accumulating uncertainty along the way. The first major tool astronomers used to trace the Milky Way's spiral structure was radio astronomy, specifically the observation of hydrogen gas at a wavelength of 21 centimeters. Hydrogen is the most abundant element in the universe, and it is distributed throughout the interstellar medium in enormous quantities. Neutral hydrogen atoms, under certain quantum mechanical conditions, emit radio waves at a very precise wavelength of 21 centimeters. This emission can pass through the dust clouds that block visible light, meaning radio telescopes can detect hydrogen gas across vast distances of the galaxy that would be completely opaque to optical instruments. By observing this 21 centimeter emission and measuring the Doppler shift of the radio waves, astronomers could determine how fast each cloud of hydrogen gas was moving toward or away from us. Since the gas orbits the galactic center at speeds that depend predictably on its distance from the center, the measured velocity could be used to estimate how far away each cloud was. Map enough clouds, and you could trace the large-scale distribution of hydrogen throughout the galaxy and infer the locations of the spiral arms. This technique,
molecular
called
clouds,
the
stars are
kinematic
born.
distance method,
Massive
was a
orbital
genuine
star
achievement.
explodes as a supernova.
It allowed astronomers to map the distribution of gas throughout much of the Milky Way using observations made entirely from within it. But it had serious limitations that became more apparent as the maps were refined and compared compared with other lines of evidence. The kinematic distance method rests on an assumption. It assumes that the galaxy rotates in a smooth, regular, predictable fashion, and that the relationship between a gas cloud's distance from the galactic center and its orbital velocity follows a well-behaved pattern called the rotation curve. In practice, the galaxy does not rotate perfectly smoothly. Individual clouds of gas have their own local motions superimposed on their general orbital motion. A cloud might be falling toward a massive stellar complex, or expanding outward from a recent supernova, or caught in the gravitational influence of a nearby dense region. These local motions add velocity components that the kinematic distance method cannot distinguish from the orbital velocity, and they translate directly into errors in the estimated distance. Near the galactic center and near the Sun's own orbital radius, the method becomes even less reliable. At distances from the center similar to our own, a given measured velocity can correspond to two different possible distances, one on the near side of the orbit and one on the far side, and without additional information, it can be impossible to determine which is correct. The method produces an ambiguity that requires independent evidence to resolve. For the Orion Arm specifically, this problem is particularly acute. The kinematic distance method works best for features that are clearly separated in velocity from our own local standard of rest.
This is an external galaxy seen cleanly
well
from outside.
inside or well
In contrast,
outside
our
our
own galaxy is
orbital
observed from
radius
within through obscuring
produce
dust and gas.
distinctly shifted radio signals that are relatively straightforward to interpret. Features at roughly our own distance from the galactic center, which is precisely where the Orion Arm sits, produce signals that are difficult to interpret unambiguously. The arm we are trying to map is located in exactly the region where our primary mapping technique is least effective. We are trying to measure the room we are standing in with an instrument that works best at a distance. The second major approach used optical and infrared astronomy to trace spiral structure through the positions of bright young stars and the ionized hydrogen regions surrounding them. Massive young stars are so luminous that they can be seen across thousands of light years, and they tend to concentrate in spiral arms where the density waves trigger star formation. By cataloging the positions of these objects and measuring their distances, astronomers could trace the arms through the young stellar population. But distance measurement in optical astronomy carried its own substantial uncertainties. Before precise parallax measurements became available, most stellar distances were estimated through a technique called spectroscopic parallax, which involves determining a star's spectral type from its light, inferring its intrinsic luminosity from that spectral type, and then comparing the inferred luminosity to the star's apparent brightness to calculate how far away it must be. This method is broadly reliable, but carries uncertainties that can reach 30% or more, particularly for very distant or unusual stars. A 30% uncertainty on a distance of 5,000 light years means the star could be anywhere between 3,500 and 6,500 light years away. When you are trying to map the detailed structure of a spiral arm, errors of this magnitude are deeply problematic. Features that appear to be at the same distance might actually be separated by thousands of light years. Connections between structures that seem real on the map might be artifacts of overlapping distance uncertainties. The boundaries of an arm, where it fades into the interarm region, become impossible to trace with any confidence. It was in this environment of genuine but limited knowledge that the traditional picture of the Orion Arm emerged, a short, modest spur. A minor connector between the Sagittarius Carina arm on the inside and the Perseus arm on the outside. Roughly 10,000 light years long, perhaps somewhat shorter in some models. A secondary feature, without the grandeur or extent of the major arms. The diagrams that encoded this picture became standard. They were reproduced in textbooks and documentaries and educational materials for decades, and the impression they created of the Orion Arm as a thin, minor bridge became fixed in the public understanding of our galactic neighborhood. Then, in December of 2013, the European Space Agency launched a spacecraft called Gaia. Gaia's mission was deceptively simple in concept and staggeringly ambitious in execution. It was designed to measure the positions, distances, and motions of stars across the Milky Way
In
with a precision
1181,
that no
East Asian
previous
astronomers
instrument
observed
had
a bright guest
approached.
star in
The technique it
Cassiopeia,
uses is
linking it
called
to the modern
astrometric
nebula
parallax, and it is based on a principle so straightforward that it can be demonstrated with one eye closed and a finger held at arm's length. Close one eye, hold up a finger, and note which background
Built
objects
after
it
the
appears to be in front
1572
of.
supernova,
Now switch eyes
Urana
without
Borgon
moving your
Pond
finger.
Medfreni.
The finger appears to shift against the
Nova
background
Stella,
because
work
you
that
are
gave
now
us the
viewing
word
it from a
nova
slightly
and began
different
the
position.
modern understanding
The
of
amount of
stellar
that
change.
apparent shift tells you how far away the finger is. The farther away the finger, the smaller the shift. This is parallax. As the Earth orbits the Sun, our position in space changes by the diameter of Earth's orbit, about 300 million kilometers, between observations made 6 months apart. Nearby, stars appear to shift slightly against the background of much more distant stars as we observe them from these different positions. The amount of the shift is directly related to the star's distance. Measure the shift precisely, and you have a direct geometric measurement of distance that requires no assumptions about the star's brightness, temperature, or spectral type. The problem is that even for relatively nearby stars, the parallax shifts are extremely small. For a star 100 light-years away, the shift is about 32 thousandths of an arcsecond. An arcsecond is 1/3600th of a degree. 32 thousandths of an arcsecond is a fantastically tiny angle. Measuring it from the ground is nearly impossible because the Earth's atmosphere blurs starlight in ways that swamp the signal. From space, above the atmosphere, with a carefully designed instrument and a patient observing strategy, it becomes possible. Gaia was built to measure parallax shifts as small as a few millionths of an arcsecond. This precision, almost incomprehensible in its fineness, translates to reliable distance measurements for stars thousands of light-years away. Over its operational lifetime, Gaia has measured positions, parallaxes, and proper motions, the slow drift of stars across the sky over time, for nearly 2 billion individual stars. 2 billion. The catalogue Gaia has produced is the most detailed and comprehensive map of stellar positions and distances ever assembled. It has transformed our ability to study the Milky Way's structure in ways that were simply not possible before. The results that have emerged from Gaia data regarding the Orion Arm have been striking. Multiple independent research teams, working with different stellar populations and different analytical methods, have found that the arm extends considerably farther than traditional estimates suggested. Studies tracing the arm through populations of young stars, through open clusters of recently formed stellar groups, through classical Cepheid variable stars, which are particularly valuable distance markers because their pulsation periods are directly and precisely related to their intrinsic luminosities, have consistently found that the Orion Arm reaches beyond the 10,000 light-year figure that appeared in older models. Some analyses trace the arm to 15,000 light-years. Others suggest it may extend to 20,000 light-years or beyond in certain directions. The exact figure depends on how the arm's boundaries are defined, which stellar population is used as a tracer, and how the data are interpreted in regions where the arm structure becomes less distinct. But the convergence across multiple studies using independent methods points in a clear direction. The Orion Arm is larger than we thought. The pitch angle of the Orion Arm, the angle at which it is inclined relative to the galaxy's circular structure as it spirals outward, has also been measured more precisely using Gaia data than was previously possible. The pitch angle matters because it is one of the properties that distinguishes genuine spiral arms from random concentrations of stars or minor interarm features. A true spiral arm, part of the galaxy's coherent density wave pattern, should have a pitch angle consistent with the overall spiral geometry of the galaxy. The measured pitch angle of the Orion Arm, approximately 10 to 12 degrees, falls within the range measured for the galaxy's confirmed major arms.
Only its
This is
radio
not
and
what you would
X-ray
necessarily
emissions escape,
expect from a random
revealing the
spur
explosion
or minor
decades later.
interarm clumping. It suggests the Orion Arm is a genuine component of the Milky Way's spiral pattern, not merely a local density fluctuation between two larger features. Complementing the Gaia
This is an
data,
external galaxy,
measurements of
seen cleanly from
masers have
outside.
provided
In
another
contrast, our own
independent line
galaxy
of
is observed
evidence
from
about
within
the
through
Orion
obscuring
Arm
dust and
structure.
gas.
Masers are natural sources of microwave amplification by stimulated emission of radiation, occurring in regions of active star formation where specific molecular transitions produce intense, narrowly focused beams of microwave radiation. Because they are associated with star formation, masers tend to be located in spiral arms. And because the microwave emission they produce is extremely precise in frequency, it can be measured with extraordinary accuracy using a technique called very long baseline interferometry, which combines data from radio telescopes spread across thousands of kilometers of the Earth's surface, or even between ground-based and space-based instruments, to achieve angular resolutions far finer than any single telescope could achieve alone. Using very long baseline interferometry, astronomers have measured the parallaxes and proper motions of masers in various parts of the Milky Way, with a precision comparable to Gaia's optical measurements. The maser data for objects within the Orion Arm confirm that it is a coherent, elongated structure extending across thousands of light years, with the internal kinematics, the pattern of how stars and gas within it are moving, consistent with a genuine spiral arm rather than an unstructured collection of stars. The masers trace a clear spiral feature with consistent orientation and extent, reinforcing the picture emerging from Gaia's stellar data. The project that has coordinated many of these maser measurements, called the Bar and Spiral Structure Legacy Survey, or BESSL, has been systematically mapping the Milky Way's spiral structure using masers across the galaxy. Its results have repeatedly found that the Milky Way's spiral features are more structured and more coherent than older radiokinematic maps suggested. The Orion Arm, in the BSL data, appears as a well-defined feature with clear spatial extent and consistent internal dynamics. What does all of this mean for how we understand the Orion Arm? It means the traditional classification of the Orion Arm as a minor spur, a thin connector, a secondary feature of limited extent, needs to be revised, not abandoned entirely. The Orion Arm is still shorter than the Perseus Arm and less massive than the Scutum-Centaurus Arm. Those relationships have not changed, but the specific picture of a stubby bridge, a mere 10,000 light-years long, sitting passively between two grand spiral arms, appears to understate the structure's true character. Some astronomers now prefer to refer to it as the local arm rather than the Orion spur, a naming choice that reflects its upgraded status in current models. Others maintain the spur designation while acknowledging that it is larger and more coherent than earlier estimates indicated. The terminology debate will likely continue as more data accumulate and as different research groups apply different criteria for what constitutes a full arm versus a spur versus a branch. But the substance beneath the terminology debate is clear. The Orion Arm is a more significant structure than the standard diagrams have communicated. It may be half again as long as traditional estimates, or even twice as long. It has a pitch angle consistent with genuine spiral arm membership. Its internal dynamics show the coherence of a real density wave feature.
Built after the 1572 supernova,
mapped now with the precision that Gaia makes possible, extend farther and in greater detail than any previous instrument had revealed. Consider what it means that our best estimate of the Orion Arm's length has grown simply because our instruments improved. We did not move, the arm did not change, the stars within it did not shift. What changed was our ability to measure where they actually are. The arm was always this large. We simply lacked the tools to see its full extent. Every diagram drawn before Gaia was working with incomplete information, and that information consistently underestimated the structure we were trying to depict. This is a pattern that recurs throughout the history of astronomy. Every time observational precision improves, the universe turns out to be larger, more complex, and more structured than previous measurements had suggested. The history of cosmology is in many ways a history of scale being revised upward. Edwin Hubble's measurements in the 1920s revealed that the fuzzy nebulae visible in telescopes were not nearby gas clouds within the Milky Way, but entirely separate galaxies, each one containing billions of stars, separated from us by millions of light years. That single revision expanded the known scale of the universe by a factor of millions. The discovery that the universe is not merely expanding but accelerating in its expansion, announced in 1998 and recognized with the Nobel Prize in 2011, added another layer of scale and complexity to the cosmological picture that no one had fully anticipated. The revision to our understanding of the Orion Arm's extent is smaller in scope, a local adjustment rather than a cosmological revolution, but it follows the same pattern: better data, larger structure, more precise measurements, more significant feature. The universe at every scale of examination consistently exceeds what our previous tools allowed us to see. And what the revised picture of the Orion Arm shows us is this: our home in the galaxy is not the modest, unimportant spur that generations of textbook diagrams have depicted. It is a substantial spiral feature, potentially twice the size of older estimates, with the structural characteristics of a genuine arm rather than a minor interarm bridge. It sits between two larger arms, certainly. It is less massive and less active than the Scutum-Centaurus or Perseus arms, certainly. But it is a real feature of the Milky Way spiral pattern, one that extends for 15,000, perhaps 20,000 light-years, one that contains billions of stars and hundreds of millions of worlds, one that has its own internal structure and its own star-forming regions, and its own complex history of stellar generations shaping the interstellar environment. The Sun is not in a galactic footnote. It is in a genuine arm of the Milky Way, an arm smaller than the most prominent ones, quieter, less turbulent, perhaps more hospitable to the kind of long-term planetary stability that life requires. But an arm nonetheless, a structure that belongs to the galaxy's spiral architecture as fully as any other feature, and one whose true dimensions have only now, with the most precise stellar measurements in human history, begun to come into focus. But we have not yet placed this revised and expanded Orion Arm into its full context. We have looked inward at its contents and outward at its extent. We have examined the local bubble nested within it, and the billions of worlds distributed throughout it, and the ancient stellar generations that shaped its interstellar environment. What we have not yet done is step back far enough to see the Orion Arm in relation to the whole galaxy, to see it alongside the Perseus Arm and the Scutum-Centaurus Arm and the galactic center and the full 100,000 light-year disk of the Milky Way, to see it as one feature among many, and to understand what that relationship truly reveals about the scale of everything we inhabit. That is where we go next.
Only its radio
Place
and
the
X-ray
Orion Arm
emissions
next to
escape,
the Perseus Arm,
revealing the
and
explosion
something
decades
uncomfortable
later.
happens to your sense of scale. The Perseus Arm stretches for somewhere between 30,000 and 40,000 light-years along its length. Some models place it longer, tracing its spiral arc across an even greater fraction of the galaxy's circumference before its stellar populations fade into the interarm regions beyond. It is one of the two primary arms in most structural models of the Milky Way, a dominant feature of the galaxy's disk, rich with star-forming regions and young stellar populations and enormous molecular clouds churning out new suns at rates that dwarf anything occurring in our quieter neighborhood, 30 to 40,000 light-years. The Orion Arm, even in the revised estimates that Gaia data has produced, reaches perhaps 15 to 20,000 light-years. The Perseus Arm is roughly twice as long. On a galaxy diagram, this difference is immediately visible. The Perseus Arm sweeps across a substantial arc of the diagram, a bold and prominent curve. The Orion Arm sits beside it as a shorter, thinner feature. Your eye registers the difference and draws the obvious conclusion, but consider what the comparison actually contains. The Perseus Arm is longer. That is true. Yet the Orion Arm, at 15 to 20,000 light-years in the updated picture, is itself a structure that light needs 15 to 20,000 years to cross. A beam of electromagnetic radiation traveling at the absolute maximum speed the universe permits would require somewhere between 15 and 20 millennia to traverse our arm from end to end. The Perseus Arm being twice as long means a beam of light needs 30 to 40 millennia to cross it. Both numbers are so far beyond anything in human experience that the difference between them while real and significant in astronomical terms, produces no meaningful distinction in terms of human comprehension. Both are equally, completely, and permanently beyond our reach. This is the paradox that galaxy diagrams create. They show you a real difference. The Perseus Arm genuinely is larger than the Orion Arm, and your brain processes that real difference using the same cognitive machinery it uses to distinguish a large rock from a small pebble. But the machinery is not calibrated for these magnitudes. When both objects are incomprehensibly large, the fact that one is larger than the other does not make the smaller one comprehensibly small. It makes it somewhat less incomprehensibly large. That is not the same thing, and no diagram, however carefully constructed, can prevent your visual system from treating the smaller feature as small when it sits beside a larger one. Think of two mountains. One rises 8,000 meters above sea level, the other rises 4,000 meters. Photographed side by side from a distance, the shorter mountain looks, proportionally, half the height of the taller one, and your brain correctly registers it as shorter. But would anyone look at a 4,000-meter peak and call it a minor hill? Would anyone standing at its base, looking up at rock faces rising thousands of meters above them, generating their own weather systems in the cold air of the upper elevations, conclude that this was an insignificant feature of the landscape? No, 4,000 meters is a mountain. The fact that a taller mountain exists nearby does not change that. The Orion Arm is a 4,000-meter mountain sitting next to an 8,000-meter mountain, shorter certainly, but still a mountain. The Sagittarius Carina Arm, which lies inward from our position between us and the galactic center, presents a similar comparison. It extends for at least 30,000 light-years, possibly more, sweeping around a significant portion of the galaxy in the curving arc that gives it its name. The Sagittarius Arm contains some of the most spectacular and actively studied objects in the Milky Way. The Eagle Nebula, made famous worldwide by the Hubble Space Telescope's 1,995 image of the pillars of creation, those towering columns of gas and dust sculpted by the radiation of nearby young stars, sits in the Sagittarius Arm at roughly 7,000 light-years from Earth. The columns themselves, the pillars of creation, are several light-years tall, individual structures within a single nebula inside a single arm of the galaxy, and they stand several light-years in height. The Omega Nebula, also called the Swan Nebula, is another massive star-forming region in the Sagittarius Arm, located approximately 5,000 to 6,000 light-years away. It contains a cluster of young, massive stars whose combined radiation illuminates and sculpts the surrounding gas cloud into luminous forms that span dozens of light-years. These are not small objects inside a large arm, they are large objects inside a vast arm. The scale compounds at every level. Then there is the Scutum-Centaurus Arm. By most measures, this is the most massive and prominent spiral arm in the entire Milky Way. It emerges from one end of the galaxy's central bar, where gas funneled inward along the bar's length becomes compressed and triggers explosive bursts of star formation, and it sweeps outward in an enormous arc that may extend 60,000 light-years or more before fading into the galaxy's outer regions. Some models suggest the Scutum-Centaurus Arm and the Perseus Arm together constitute the two primary arms of the Milky Way, with everything else, including the Sagittarius Carina Arm and the Orion Arm, representing secondary or connecting features between them. 60,000 light-years. The Scutum-Centaurus Arm, at 60,000 light-years, is 3 to 4 times the length of the Orion Arm, even in the most generous current estimates. It contains some of the most luminous stellar clusters in the galaxy. The Westerlund, one cluster, sitting within the Scutum-Centaurus Arm at roughly 15,000 light-years from Earth, is one of the most massive young stellar clusters known in the Milky Way, containing thousands of hot, massive stars packed into a region only a few light-years across. The combined luminosity of the stars in Westerlund 1 is millions of times the luminosity of the Sun. It is a stellar metropolis, a concentration of stellar energy so intense that if it replaced our Sun at the same distance, the night side of Earth would be brightly lit. The Norma Arm, positioned closer to the galactic center than our location, sits in a region of higher stellar density where the gravitational environment is more intense and the interstellar medium is more compressed. It is associated with some of the most active star-forming regions in the inner galaxy, regions where the proximity to the galactic center and the influence of the central bar drive gas compression rates that far exceed anything in the Orion Arm's quieter environment. And anchoring the entire system at the center of it all is the galactic bar, that elongated structure of old stars cutting through the heart of the Milky Way, roughly 27,000 light-years from end to end. The bar alone, this single structural element of the galaxy's center, spans nearly twice the length of the Orion Arm. It contains billions of old red and orange stars, concentrated into a beam-shaped formation that has persisted for billions of years. At each end of the bar, the major spiral arms emerge and spiral outward, defining the galaxy's overall shape. Surrounding the bar is the galactic bulge, that dense spheroidal concentration of old stars approximately 10,000 light-years across. The bulge alone, in its full extent, matches the traditional estimate of the Orion Arm's length. These two structures, the Orion Arm and the galactic bulge, comparable in one dimension of their size, could not be more different in character. The bulge is ancient, dense, crowded with stars so tightly packed that the night sky from any world within it would blaze continuously. The Orion Arm is younger in its stellar populations, more diffuse, quieter, shaped by the ongoing cycle of stellar birth and death that characterizes spiral arm environments. Same rough scale, utterly different environments, both inside the same galaxy. At the very center of the bulge, inside the dense concentration of ancient stars, sits Sagittarius A star, the supermassive black hole at the Milky Way's heart. Its mass is approximately 4 million times the mass of our Sun, compressed into a region smaller than our solar system. The gravitational influence of this object shapes the dynamics of the entire galactic center region. Stars orbit it at extraordinary velocities. One star, designated S2, completes an orbit around Sagittarius A star every 16 years, reaching speeds of approximately 3% of the speed of light at its closest approach. 3% of the speed of light, 9,000 kilometers per second. Our Sun, moving at 230 kilometers per second around the galactic center, is traveling at roughly 1/40th of S2's peak velocity. The gravitational environment near the galactic center is orders of magnitude more extreme than anything we experience in the Orion Arm's quiet neighborhood. Sagittarius A star is 26,000 light-years from us. That distance, which takes light 26,000 years to cross, is itself more than twice the traditional estimate of the Orion Arm's length and comparable to the revised estimates. The galactic center sits at a distance from us that matches the arm we live in. Everything inward from our position, between us and that distant core, contains the Sagittarius Carina arm, the Norma arm, the inner regions of the galactic disk, the central bar, and the bulge itself. All of that complexity, all of those structures, compressed into the 26,000 light-years of space between our position and the black hole at the galaxy's heart. Now, step back further. The Milky Way's disk extends to roughly 50,000 light-years from the galactic center in all directions, giving the galaxy a total diameter of approximately 100,000 light-years. Some recent studies suggest the disk may be larger, possibly extending 60 or even 80,000 light-years from center to edge in some directions, warped and flared in ways that older models did not fully account for. But 100,000 light-years is the traditional figure, and it is sufficient to establish the proportions we need. The Orion Arm at 20,000 light-years, the upper end of current revised estimates, represents approximately 20% of the galaxy's diameter. 1/5. It spans from our position inward partway toward the Sagittarius Arm and outward partway toward the Perseus Arm, covering a meaningful fraction of the galaxy's radial extent in our orbital neighborhood. 20% of 100,000 light-years sounds like a substantial fraction, and in absolute terms, 20,000 light-years is a genuinely enormous distance, but the remaining 80% of the galaxy's diameter contains structures that dwarf the Orion Arm in every dimension. The major arms curl around the full circumference of the galaxy in arcs that cover far more distance than any straight-line diameter measurement can capture. At our orbital distance from the center, approximately 26,000 light-years, the full circumference of the orbit is roughly 160,000 light-years. The Perseus Arm may extend across a quarter or more of that circumference. That is 40,000 light-years of arc, following the curve of the spiral, and the Orion Arm at 20,000 light-years covers perhaps 1/8 of the same circumference. 1/8. 1/8 of the circumference of our orbital ring around the galactic center. That is the Orion Arm's footprint in the galaxy. Still enormous in absolute terms, still a region of space that light needs 20,000 years to cross, but 1/8 of a much larger circle, nested within a disk that extends 50,000 light-years in every direction from the center, embedded in a structure that contains hundreds of billions of stars. And now step back further still. The Milky Way is one galaxy. There are others, many others. The nearest large galaxy to our own is the Andromeda Galaxy, known to astronomers as Messier 31. Andromeda is a spiral galaxy broadly similar to the Milky Way, perhaps somewhat larger, containing perhaps 1 trillion stars, compared to our galaxy's several hundred billion. It sits approximately 2.5 million light-years from the Milky Way. 2.5 million light-years. The Orion Arm, at 20,000 light-years in revised estimates, is 1% of the distance to Andromeda. If you scaled the Milky Way down to the size of a dinner plate 30 centimeters across, Andromeda would be another dinner plate sitting roughly 9 meters away. 2 plates, 9 meters apart, and the Orion Arm on that 30-centimeter plate would be a smear of ink approximately 6 millimeters wide. A smear of ink 6 millimeters across, containing billions of stars and everything humanity has ever known. The Milky Way and Andromeda are the 2 largest members of a collection of galaxies called the Local Group. The Local Group contains more than 50 galaxies in total, most of them small dwarf galaxies orbiting the Milky Way or Andromeda as satellites, but the group as a whole spans roughly 10 million light-years in its full extent. 10 million light-years. The Orion Arm, at 20,000 light-years, is 0.2% of the diameter of the Local Group. The Local Group is itself a member of a larger structure. The Virgo supercluster, also called Laniakea, is a vast filamentary supercluster of galaxies containing thousands of individual galaxies in dozens of galaxy groups and clusters. At its heart sits the Virgo cluster, a dense concentration of galaxies approximately 54 million light-years from the Milky Way. Laniakea as a whole spans roughly 500 million light-years. The Orion Arm is 0.04% of the diameter of the supercluster we inhabit, and Laniakea is one supercluster among many. The observable universe, the portion of the universe from which light has had time to reach us since the Big Bang, spans approximately 93 billion light-years from edge to edge. It contains an estimated 2 trillion galaxies, 2 trillion individual collections of stars, each one containing hundreds of billions of suns, each one potentially containing billions of worlds, each one a structure comparable in scale to the Milky Way, all of them distributed across a volume of space so vast that the human mind has no framework for approaching it. The Orion Arm within this hierarchy is a feature so small that it vanishes before you reach the second level of the cascade. At the scale of the Local Group, the Orion Arm is invisible. At the scale of the Virgo supercluster, the entire Milky Way is invisible. At the scale of the observable universe, the Virgo supercluster is invisible. Each upward step in scale erases the previous level completely. The cascade is relentless, and it never reaches a ceiling that the human mind can rest against and feel it has arrived at something comprehensible. But here is what the cascade also reveals. If you are willing to stay with it, rather than retreating into comfortable numbness, at every level of this hierarchy, the structures are real. The Orion Arm is real. It has physical dimensions and physical contents, and a physical history stretching back billions of years. The Milky Way is real, the local group is real,
In contrast, our own galaxy is
is
observed from
real.
within, through
The
obscuring
cosmic
dust and
web of
gas.
filaments and voids that organizes matter on the largest scales is real. None of these structures is diminished by the existence of larger ones. A river is not made less real by the existence of an ocean. A mountain is not made less significant by the existence of a continent. The Orion Arm sits at the bottom of this cascade of scales, the smallest identifiable feature in a hierarchy that reaches to the edge of the observable universe, and yet it contains everything we are. Every human who has ever lived, every thought that has ever been thought, every piece of music ever composed, every structure ever built, every word ever written, every moment of joy or grief or wonder or terror that any conscious being on Earth has ever experienced. All of it happened inside the Orion Arm. All of it happened in the 6mm smear on the dinner plate, the 1% of the distance to Andromeda, the 1/8 of the circumference of our orbital ring around the galactic center, the smallness of our location in the cosmic hierarchy, and the fullness of what that location contains exists simultaneously, without contradiction. We are cosmically insignificant by position and cosmically extraordinary by content. Both things are true at the same time. The universe does not offer a resolution of that tension. It simply presents both facts and leaves you to hold them together. Now there is one final thing to understand before this journey reaches its end. We have talked about the Orion Arm from the outside
It sent the
in
Crab
diagrams
pulsar.
and measurements and comparisons.
Its beams connect
We
that
have
ancient
talked about
event
what
to
it
the living remnant
contains
today.
and how large it is and where it sits in the galaxy. But we have not yet talked about what it means to be inside it, not as an abstract position on a map, as a physical reality, as the actual lived condition of every human being who has ever drawn breath on this planet. You are not near the Orion Arm. You are not adjacent to it or orbiting around it or traveling toward it. You are inside it. The atoms of your body are inside it. The air you are breathing right now is inside it. The ground beneath you and the sky above you and the light entering your eyes at this moment are all inside the Orion Arm. You've never been anywhere else. No human being has ever been anywhere else. Everything that has ever been called human experience has unfolded within the boundaries of this one structure.
SN
And what that
1987A,
means, truly
closest
means,
supernova.
is something
Its
that
ring
all
of
the
shock
numbers
gas
and
continues to
comparisons in the
grow.
world
February
can approach, but
1987.
never fully deliver.
A
It
massive
requires
dark
something different,
for new era
something
in
that numbers
astrophysics.
alone cannot provide. It requires looking up. Go outside on a clear night. Not a city night, not a suburban night where the orange glow of streetlights washes the sky into a featureless grey. A truly dark night, far from artificial light, in a place where the atmosphere above you is clean and still. Let your eyes adjust. Give them 20 minutes, 30 if you can, allowing the pupils to open fully and the retinal cells sensitive to dim light to reach their maximum sensitivity. And
Southwestern
then look up.
petrotraversity
What you will
star,
see, stretching
with the
from one
infrasound
horizon to the
process.
other in a soft,
In
uneven
1181,
band of
East Asian
pale
astronomers
luminescence
observed a bright
is
guest
the
star in
Milky Way.
Cassiopeia,
Not a
linking it to the
photograph of
modern
it,
nebula
not an
Gaia.
artist's rendering, the actual thing. The interior of the structure we have been discussing, seen from within,
lord, the guest
with your
star
own
blazes
eyes,
brighter than Jupiter,
using the
the heavens
same
command
biological
diligence in the eastern
instruments
sky,
that
they
every
say
human
Tauri.
being who
Built
has ever
after the
lived on this planet
1572
has used to
supernova,
observe the
Uranoborg
same sight
on Han
across
met Brent.
hundreds of thousands of years of our
The Nova
existence.
Stella,
That
the
band
word
of
that gave
light
us the word
is
nova,
not a feature
and
of
began
the
the modern
sky in
understanding
the
of
way
stellar
that clouds
change.
are features
Behold
of the
the
sky.
supernova of
It is not
1604.
weather,
This
it
shatters
is
the
not
immutable spheres of
atmosphere,
Aristotle.
it is
A new
depth.
truth emerges.
It is the accumulated
Kepler
light of
observed the
billions of
1604
stars
supernova.
so
The
far
telescope
away
arrived,
that your
but
eyes
too
cannot
late to
resolve
witness
them
it.
individually, blurred together by distance into a continuous, luminous haze. You are not looking at a
In late
surface.
2019,
You are
Betelgeuse
looking into a
worldwide stars
volume,
mysteriously
a
dipped
volume
by
of
early
space
2020.
that
Betelgeuse
extends
started its
thousands
slow
of light
recovery.
years in the direction your eyes are pointed, packed with stars that your visual system cannot separate because the angular distances between them, at their true distances, fall below the resolving power of the human eye. What your brain processes as a soft glow is actually billions of individual nuclear furnaces, each one a sun, many of them larger and more luminous than our own, all of them so remote that their individual identities dissolve into collective radiance. That is the Orion Arm, seen from the inside. Every culture in human history that has lived under dark skies has looked at that band and tried to make sense of it. The ancient Greeks called it the Milky Way, believing it was milk spilled across the sky by the goddess Hera when the infant Heracles drank too forcefully at her breast. Aboriginal Australians saw it not as a feature of the background sky, but as a dark river defined by the dusty clouds silhouetted against the stellar light, and they read stories in those dark patches that astronomers now recognize as the dense molecular clouds of the inner galaxy blocking the light from stars behind them. The Khoisan people of southern Africa imagined it as scattered embers from an ancient fire, still glowing faintly in the darkness above. The Pawnee people of North America understood it as a path traveled by the spirits of the dead on their way to another existence. None of them knew what it was. None of them knew they were looking at a spiral arm of a barred spiral galaxy, a structure 10,000 to 20,000 light-years in extent, containing billions of stars and an unknown but probably vast number of worlds. None of them knew the light reaching their eyes had been traveling for thousands of years before it arrived. None of them knew they were themselves made of the material they were observing, that the atoms of their bodies had been forged in earlier generations of the very stars they were contemplating. But they looked, every single one of them looked, across all the variety of human cultures and human histories and human belief systems, across all the differences of language and geography and circumstance. Human beings have stood under the night sky, looked at that band of pale light, and felt something that the different traditions encoded in different ways, but that seems to have been, at its core, the same experience. A sense of something immense and ancient. A sense of one's own smallness in relation to something incomprehensibly large. A sense, perhaps, that the darkness above contained more than could be seen or understood, and that the attempt to see and understand it was worth making anyway. That impulse, the impulse to look up and ask what is there, is one of the most distinctively human things about us. Other animals see the night sky. Some of them navigate by it. But as far as we know, no other animal on Earth has looked at the stars and wondered about their nature, their distance, their composition, their histories. No other animal has built instruments to examine them more closely, developed mathematics to describe their motions, sent spacecraft toward them, or spent centuries of collective intellectual effort trying to understand the structure of the galaxy they inhabit. That combination of curiosity and capability, the drive to ask questions about things beyond immediate necessity, and the ability to actually make progress toward answers, appears to be unique to us, at least on this planet, at least as far as we currently know. And what has that curiosity produced? It has produced the knowledge that the band of light crossing the sky is not spilled milk or scattered embers or a river of souls. It is the interior of the Orion Arm. It is the combined light of stars that formed from molecular clouds distributed across thousands of light-years of space, each one a gravitational collapse, a nuclear ignition, a sustained fusion reaction converting hydrogen into helium, and releasing energy that has been traveling through space for longer than any human civilization has existed before reaching your retina in this moment. It has produced the knowledge that the arm you are looking into is 10,000 to 20,000 light-years in extent, that it contains billions of stars and probably tens of billions of worlds, that it sits between two larger spiral arms in a barred spiral galaxy 100,000 light-years across, that the galaxy itself is one of 2 trillion in the observable universe, that the universe has been expanding for approximately 13.8 billion years from a state of extraordinary density and temperature in the event we call the Big Bang, and that the atoms in your body were produced in the stellar furnaces of earlier generations of stars and scattered through the interstellar medium by their deaths before being gathered by gravity into the cloud that became the sun and the Earth and everything on it. You are made of the Orion Arm, not poetically, not metaphorically. The carbon in every cell of your body was synthesized in the core of a star that existed somewhere within this structure before the solar system formed. The oxygen you are breathing was produced in stellar interiors and distributed through the galaxy by stellar winds and supernova explosions. The calcium in your bones, the phosphorus in your DNA, the iron carrying oxygen through your bloodstream right now, every element heavier than hydrogen and helium in your body was forged in a star, and the stars that forged them lived and died within the Orion Arm. When you look up at that band of pale light, you are not looking at something external to yourself. You are looking at the source, the factory, the ancient stellar population from which you are descended in the most literal chemical sense. The stars you see are not your ancestors in any biological meaning of the word, but they are your ancestors in the elemental sense. Without them, without their lives and their deaths, and the material they scattered through the interstellar medium over billions of years, you would not exist. The matter of which you are composed would not exist in the form it takes. The chemistry of life would not be possible without the heavy elements that stars produce. You are the Orion Arm become conscious of itself, a temporary, improbable, extraordinarily complex arrangement of atoms that originated in this arm's stellar furnaces, organized by 4 billion years of biological evolution on one small rocky planet into something capable of asking where it came from. The arm did not intend this. The universe does not have intentions, but it happened here, in this structure, on this world, in this moment of cosmic history. Matter arranged itself into something that can look back at its own origins and understand, at least partially, what it sees. That is not a small thing. That may be the largest thing. Now, return to where we began. Those galaxy diagrams, those clean, color-coded illustrations of the Milky Way viewed from above, with the sweeping arms labeled and the central bar indicated and the arrow marking our position in the Orion Arm, those diagrams that generations of students have glanced at and absorbed a single impression from. We live in a minor part of the galaxy, a spur, a secondary feature, a thin bridge between two grander structures. You know now what those diagrams have been hiding. Not through any deception, but through the sheer impossibility of representing galactic scale on a medium that human eyes can take in. Every centimeter of those diagrams represents thousands of light years of actual space. The 3 or 4 centimeters assigned to the Orion Arm contain 10,000 to 20,000 light years of distance, billions of stars, hundreds of millions of worlds, the entire visible night sky, every object ever studied by human astronomers within our galaxy, the local bubble and its ancient supernova-carved walls, the molecular clouds where new stars are being born right now, the supernova remnants expanding outward from stellar deaths that human beings witnessed and recorded, the star-forming nebulae where future solar systems are assembling themselves from raw gas and dust, and every human being who has ever existed. The diagram shows you proportion. It cannot show you magnitude. And magnitude is everything. The Orion Arm is not small. It has never been small. It only appears small because the thing it sits inside is so extravagantly, so unreasonably, so incomprehensibly large that even a structure spanning tens of thousands of light years registers as a minor feature when compressed onto a page. The galaxy is a monster of scale. The Orion Arm is enormous. Both of these things are true simultaneously, and neither one cancels the other out. What you should carry forward from this journey is not a set of numbers to recite. The numbers matter, and they are worth knowing. 10,000 to 20,000 light years, several billion stars, hundreds of millions of potentially habitable worlds, 26,000 light years from the galactic center, 230 kilometers per second orbital velocity, 250 million years per galactic orbit. These are real facts about the place you live, and knowing them is better than not knowing them. But numbers alone do not produce understanding. Understanding requires something more. What produces understanding is the moment when a number stops being a number and starts being a place. When 10,000 light years stops being an entry in a table of galactic dimensions and starts being a physical reality that you inhabit, that contains you, that is in some deep sense what you are made of and where you belong. When the band of pale light across the night sky stops being a picturesque astronomical feature and starts being the interior of the structure you have been living inside for your entire existence, seen at last for what it actually is. That shift, from number to place, from abstract to inhabited, is what all of this has been building toward, not the statistics, the recognition, You live in the Orion Arm. You have always lived in the Orion Arm. Every human being who has ever drawn breath on Earth lived in the Orion Arm. Every moment of human history unfolded inside this structure. Every star that has ever guided a ship, or inspired a myth, or caused a child to go quiet with wonder, is a resident of the same arm you inhabit. The entire accumulated experience of our species, every joy and catastrophe and discovery and creation, happened here, in this arm, in this galaxy, on this one small world orbiting one ordinary star, in the inner edge of a spiral feature that diagrams have spent decades teaching you to dismiss as minor. It is not minor. Nothing that contains all of this could ever be minor. It is the place where conscious matter emerged from unconscious chemistry, where the universe's long process of structural elaboration produced, among its billions of other products, something that can look back at the process and ask how it works. That is what the Orion Arm has produced, among everything else it contains. That is what you are. The next time you encounter one of those galaxy diagrams, the next time you see the Milky Way drawn on a screen or a page with the spiral arms sweeping grandly outward and a small marker indicating our position in the Orion Arm, do not let your eye pass over it in half a second on its way to the more impressive-looking features. Stop. Stay with it. Remember what those few centimeters actually represent. Remember that inside that thin labeled sliver there are billions of suns. Remember that many of them have planets, and some of those planets are rocky, and some of those rocky worlds orbit inhabitable zones where liquid water might pool on solid ground. Remember that the distance from one end of that sliver to the other is so vast that the fastest thing in the universe needs 10,000 years to cross it. Remember that you are inside it, right now, in this moment, made of its ancient stellar material, carried along in its slow rotation around the galactic center at 230 kilometers per second. And if the night is clear and you can find a place away from city light, go outside. Find the Milky Way. Let your eyes adjust until the full extent of it becomes visible, that soft river of accumulated starlight arching from one horizon to the other. Look at it not as scenery, but as home. Not as a backdrop to human experience, but as the structure that made human experience possible. Look at it knowing that you are not standing beneath it as an observer. You are inside it. You are part of it. The light reaching your eyes from those billions of distant suns is the light of your neighborhood, your arm, your place in the vast and ancient architecture of a universe that has been arranging matter into increasingly complex forms for nearly 14 billion years, and in at least one location that we know of, arranged it into something capable of looking up and wondering what it all means. The Orion Arm is not small. It only looks that way because the galaxy refuses to fit on any page without compressing everything inside it down to the width of a fingernail. But you know the truth now. You know what those few centimeters contain. They contain everything. And for all the vastness of what lies beyond them, for all the hundreds of billions of stars in the major arms and the supermassive black hole at the galactic center and the 2 trillion galaxies filling the observable universe, and whatever lies beyond the boundary of what light has had time to reach us from, for all of that immensity stretching outward in every direction without apparent limit, this one structure, this one arm, this one sliver on a diagram, is the only part of the universe that has ever, in the entire 13.8 billion year history of everything, looked back at itself and understood what it was looking at. That is not a minor feature. That is the most extraordinary thing we know of anywhere. Good night, and may the next clear sky you find remind you of exactly where you are.
Its ring of shocked gas continues to grow.